For most of human history, the Milky Way was the universe. The thought that we might live among countless other galaxies was beyond imagination. But that illusion would not last forever. The Milky Way, magnificent as it is, was never the whole story, only the closest chapter in a far greater book. When we look up at the night sky, we're not seeing the universe as it is, but as it was, a moving archive of ancient light. Every speck, every faint glow carries a fragment of the cosmos billions of years old, and hidden among those whispers of light are clues that our galaxy is just one of trillions, a single spark in an ocean, too vast for the human mind to grasp. At first glance, it sounds like a question with a simple answer. Count the galaxies, add them up, and you know how vast the universe is. But the truth hides in the nature of light itself. We can only see what has reached us, and light travels at a finite speed. Every observation is a look back in time, not a snapshot, but a memory. To measure how many galaxies exist, astronomers must peer across billions of years into epochs where light has been stretched, dimmed, and almost lost to the expanding fabric of space. Even with the best telescopes, the task is almost absurd. A galaxy isn't a fixed thing, it evolves, collides, and fades. Some vanished before their light ever arrived here. Others are so faint that no instrument on Earth can detect them. What we count are ghosts of the past, not the living cosmos as it exists today. And yet from these fragile rays of ancient light, astronomers try to piece together the impossible. A census of the universe itself, knowing full well that most of it will remain forever unseen. Every night the sky seems infinite, yet what we see is only a fraction of what exists. The stars that shimmer above are mostly neighbours, part of a thin galactic disk no thicker than a few thousand light years. Beyond that veil, the universe stretches hundreds of billions of times farther. Our naked eyes cannot see galaxies, they can only glimpse the brightest outposts of our own. For ancient observers, that horizon felt absolute. The night sky was the boundary between the known and the unknowable. But the darkness between those stars isn't empty. It's filled with light too faint for human vision radiation, so old it has been stretched into invisible wavelengths. When astronomers later aimed telescopes into these dark patches, they didn't find nothing, they found everything. Thousands of galaxies where once there seemed to be none. The quiet blackness above us was never the end of the cosmos. It was merely the surface of a vast ocean we'd mistaken for the shore. Before modern telescopes, the cosmos was a puzzle drawn on the sky. Astronomers charted the motions of stars-tracked comets and measured the faint mist of the Milky Way. Yet everything they could observe seemed to belong to a single enclosed world. Even great thinkers like Galileo and Herschel believed the stars formed one immense structure, perhaps finite, perhaps endless, but still ours alone. The idea that each faint nebula might be another island of stars was considered pure speculation, a fantasy beyond reason. Still, curiosity persisted. Some astronomers peering through their primitive instruments noticed that certain nebulae looked different, spirals, disks, or smudges too distant to resolve. They debated fiercely. Were these clouds within our galaxy, or were they island universes of their own? For centuries no one could prove it either way. The question haunted observatories like a quiet echo in the dark. Humanity stood at the edge of an immense truth, staring into it without yet knowing what it was. Science often begins not with an answer but with a doubt. By the late 19th century, that doubt had begun to glow among astronomers. Why did some nebulae appear so far away, so unconnected to our galactic plane? Why did their light behave differently from nearby stars? A few daring minds started to wonder if these strange spirals might not belong to the Milky Way at all. But such a claim would mean something unthinkable, that the universe was vastly larger than anyone had dared to imagine. That fragile doubt became the seed of modern cosmology. If these nebulae were indeed other galaxies, then our entire picture of existence would collapse and rebuild overnight. The universe would no longer be a single island, but an ocean of worlds. Yet without proof, the idea remained little more than a whisper in the halls of observatories. For now, humanity still stood at the centre of its own imagined universe, waiting for one clear observation to break the illusion forever. And so with that single doubt, humanity took its first real step toward the infinite. Every telescope is a time machine. The farther we look, the older the universe becomes. When astronomers capture the faint glow of distant galaxies, they're not seeing them as they are today, but as they were billions of years ago. Each photon of light is a traveller crossing cosmic distances to reach our eyes. A simple glance at a deep space image is in truth a glimpse into prehistory, a window through which the past still burns quietly alive in the present. It's a strange thought that light can outlive the worlds it came from. Some of those galaxies may no longer exist, their stars scattered, their shapes erased by mergers or time. Yet their light continues carrying the memory of what once was. Telescopes don't just reveal the distant universe, they reveal its persistence. Every observation is an act of time travel, a way of touching the universe, not as it is, but as it once dreamed itself to be. When astronomers speak of the observable universe, they don't mean the whole of existence, only the part that light has had time to reach us from. Beyond that invisible frontier, the universe continues perhaps endlessly. The boundary isn't physical, it's temporal, defined by the age of space itself. We're surrounded by a cosmic horizon roughly 46 billion light-years away in every direction. A sphere not of matter, but of time expanding as the universe grows older. Everything beyond that horizon remains unseen, its light still travelling through the void. One day, eons from now, even nearby galaxies will slip beyond visibility as cosmic expansion pulls them away faster than light can follow. What we call the observable universe is really just our local bubble of time, a temporary window carved out by physics and chance. And within that fragile bubble we search for meaning, counting galaxies we were never meant to see. At first it sounds simple, count what you can see and multiply, but the universe doesn't make it that easy. Every telescope, no matter how powerful, sees only a fragment of the sky. What we capture are statistical samples, not a census. Some galaxies are hidden behind dust, others lie beyond our detection threshold. Even the faintest light may be drowned out by cosmic background noise. To measure everything, astronomers must rely on models, mathematics, and a little imagination. Each observation is a clue, not a conclusion. From a small patch of deep sky, scientists estimate how many galaxies should exist across the entire celestial sphere. But the universe is not uniform. Matter clumps and thins. Voids stretch for hundreds of millions of light-years. A single deep field might represent one cosmic neighborhood, not the average of all. Counting galaxies, then, is not a matter of arithmetic. It's an act of inference, a way of sketching infinity with limited light. The deeper we look into the universe, the more deceptive it becomes. Light doesn't simply travel, it stretches, bends, and fades with distance. As space expands, the wavelength of that light grows longer, turning visible colours into red-shifted whispers from the ancient past. A galaxy seen as a tiny red smear might in truth be vast and brilliant, but its light has aged for billions of years on the way here. We see not reality, but its memory written in light. Even time itself plays tricks on what we observe. When we gaze across cosmic distances, we're witnessing events frozen in their youth, galaxies forming stars, igniting worlds, taking shape long before Earth existed. The universe we map is not the universe of now, but a mosaic of moments scattered across time. Every image is both true and outdated, a fossil record of light still arriving from the deep. To study the cosmos is to accept this distortion, to see beauty through the slow lens of eternity. To count the galaxies is to measure the scale of everything. It's humanity's quiet attempt to outline the borders of the infinite. Each new telescope from Hubble to Webb pushes that frontier a little farther, turning specks of darkness into crowded seas of light. But this is more than science, it's an act of curiosity written into our nature. We are a species that wants to know what lies beyond the horizon, even when the answer threatens to break our sense of proportion. This cosmic census is still underway. Every observation adds another piece to the map, a faint dot here, a cluster there, until the invisible begins to take shape. What once looked like a handful of galaxies now appears as hundreds of billions, perhaps trillions. Yet even as our instruments grow sharper, the universe keeps receding, its edges running away faster than our reach. To count the galaxies is to chase light itself, knowing we can never catch it. Before we could count the galaxies, we had to realize there was more than one. For centuries, astronomers believed the Milky Way was the totality of creation, an enormous but finite system containing every star, every world, every mystery. Through their early telescopes, the universe looked like a glittering shell enclosing humanity at its center. The faint clouds they saw beyond the stars were puzzling, but harmless small smudges drifting inside the limits of our cosmic home. It was an age of certainty and confinement. No one doubted that our galaxy defined the universe itself. The heavens were vast but still local, a single luminous continent surrounded by eternal darkness. And yet in quiet observatories scattered across Europe, a few restless minds began to sense something off. The stars did not end cleanly. The sky refused to fit its own borders. In that discomfort, the modern universe was waiting to be born. In the spring of 1922, men stood on opposite sides of the same sky. Harlow Shapley believed the Milky Way was enormous, so vast that it could easily contain every nebula ever seen. He placed the sun far from the center, arguing that humanity was not the focus of creation. Across from him, Heber Curtis disagreed. He claimed those faint spirals were not clouds within our galaxy at all, but entire galaxies themselves adrift far beyond its edge. Their arguments filled the halls of the Smithsonian that April. For the first time, astronomers weren't debating stars or planets. They were debating the scale of existence itself. No experiment could settle it. Telescopes were still too weak to pierce the mystery. The audience left divided, uncertain which vision of the cosmos was true. But the world had changed. Humanity had asked the right question, one that could no longer be forgotten. The universe was beginning to outgrow its walls. For centuries, the mysterious spiral nebulae were among the most puzzling objects in the night sky. Through small telescopes, they appeared as ghostly swirls of smoke, delicate, faint, and impossibly distant. Many astronomers thought they were gas clouds within our own galaxy, perhaps nurseries where new stars were forming. Others suspected something more. Their shapes were too precise, their structures too grand to be mere wisps of vapor. Still without evidence, imagination remained confined within the Milky Way. The misunderstanding was easy to forgive. In an age before photographic sensitivity or modern optics, the universe revealed itself only reluctantly. Every observation was filtered through instruments too crude to see the truth. Even the brightest of the spiral nebulae, the one in Andromeda, showed no stars under the magnification of the day. Looked smooth, featureless, too far away to resolve. The idea that this faint spiral might be a galaxy like our own was as radical then as imagining an infinity of worlds is to us now. The telescopes of the 19th century were powerful for their time, yet painfully inadequate for the questions astronomers were asking. They revealed structure but not distance, beauty but not truth. Each new lens peeled away a thin layer of mystery only to expose another one beneath. The further they looked, the more the heavens blurred into haze. It was as if the universe were teasing them, allowing a glimpse of its design, but never enough to understand its scale. Still, those crude instruments carried the first generation of explorers beyond myth. William Herschel, sweeping the sky with his massive reflectors, mapped thousands of nebulae, and believed he was charting the Milky Way's borders. He thought he was measuring the edge of creation itself. Yet even his remarkable maps told a lie. The fog he saw wasn't the boundary of our galaxy, but the threshold of countless others. The universe had hidden its enormity behind glass and patience, waiting for sharper eyes to uncover it. Long before the age of modern cosmology, many thinkers believed the universe must have an edge. The Milky Way, bright and immense, seemed to form a natural boundary, a shining wall separating existence from nothingness. Philosophers spoke of it as a kind of cosmic island, vast yet complete adrift in an endless void. It was a comforting thought, a universe small enough to be grasped, and a creation with a clear beginning and end. But nature rarely conforms to comfort. As telescopes grew stronger, that neat picture began to unravel. The Milky Way's edges blurred, stretching farther than any map could follow. Beyond its luminous band lay strange silent forms that refused to fit inside the model of a finite cosmos. For centuries, humanity clung to its island, unwilling to let go of the illusion of enclosure. Yet every new discovery was a wave breaking against that fragile shore, a reminder that infinity does not need our permission to exist. To the astronomers of the past, the sky was not a void, but a grand machine. Stars were thought to be fixed to a celestial sphere, each point of light a jewel embedded in a perfect dome. The faint mist of the Milky Way seemed like a glowing vapour, perhaps the residue of creation itself. And those strange nebulae, the spirals, the ellipses, the soft clouds were often imagined as storms in the ether, whirlpools in some invisible fluid filling space. It was a universe that felt alive, mechanical yet divine. Space was not emptiness, but a medium carrying the breath of the heavens. Gravity, light and motion were threads in a single cosmic fabric woven by unseen hands. Even when new discoveries began to challenge this view, many resisted. The idea that the universe might stretch endlessly into the dark felt cold and impersonal. People preferred the familiar warmth of a cosmos designed around them, a stage where humanity still held meaning beneath the stars. The transformation began with a single kind of star, the Cepheid variable. These remarkable suns pulse with predictable rhythm, their brightness rising and fading like a heartbeat. In the early 20th century, astronomer Henrietta Swan Leavitt discovered that the speed of their pulse was tied to their true luminosity. The brighter the star, the slower it beat. This simple relationship would become one of the most powerful tools in astronomy, a way to measure distance across unimaginable scales. For the first time, light could be turned into a ruler by comparing how bright a Cepheid appeared from Earth to how bright it truly was. Astronomers could calculate its distance with astonishing accuracy. Suddenly, the fog of space began to thin. Nebulae that had once seemed close were revealed to lie far beyond the Milky Way. The universe, once intimate and enclosed, was opening like a vast map, and at its centre, humanity stood smaller than ever, staring outward with newfound humility. Each Cepheid variable is like a cosmic lighthouse, its rhythmic pulse flashing across space with perfect consistency. Once astronomers understood this pattern, they could turn light itself into a form of geometry. The distance to any galaxy hosting a Cepheid could be measured no matter how remote. It was as if the universe had been quietly marking its coordinates all along, waiting for us to learn how to read them. And when we did, the cosmos suddenly grew thousands of times larger. That discovery unlocked the first real sense of scale. No longer was the Milky Way a self-contained world. It was just one island in a vast archipelago of galaxies. Cepheid variables became the foundation for every modern distance ladder, linking nearby stars to faraway clusters, and eventually to the entire observable universe. They are the silent code of creation, steady, patient and precise, teaching us that even in the chaos of the cosmos, order can whisper from the faintest flicker of light. Even as astronomers learned to measure distance, few could grasp what those numbers implied. If the spiral nebulae truly lay beyond the Milky Way, then the universe was incomprehensibly vast and perhaps alive with motion. Yet motion itself was forbidden by the prevailing view of the cosmos. A static, eternal structure balanced perfectly between gravity and silence. To imagine it expanding was to imagine the universe itself changing, something many found impossible, even heretical. The evidence, however, was quietly building. Spectra from distant galaxies showed subtle shifts toward red, as if their light was stretched by some invisible hand. But in the early years of the 20th century, few understood what that meant. The data was strange, the implications stranger. Astronomers gathered results without knowing they were witnessing the first signs of a moving universe. It would take one man and one mountain observatory to turn this invisible drift into a cosmic revelation. In the years just before Edwin Hubble's discovery, astronomy felt poised between wonder and doubt. The sky had been mapped, the stars measured, and yet something fundamental was missing. Every observation hinted at motion, but no one could explain what was moving or why. The universe still seemed timeless, fixed, almost comfortable in its stillness. It was an age of quiet triumph built on the illusion that humanity had nearly solved the sky. Then came the silence before the storm. Across the world's observatories, faint spectra were being recorded, each one carrying a redshift no one could fully interpret. The answers were already written in the light, waiting only for the right mind to read them. Hubble's telescope stood ready on Mount Wilson, aimed not at mystery, but at confirmation that the universe was far larger and far less stable than anyone dared to believe. The calm was about to end. High above the clouds of California on the slopes of Mount Wilson, a new eye opened to the cosmos. The Hooker telescope, 100 inches of flawless glass, was the largest ever built. When Edwin Hubble first climbed its narrow steel stairs in the early 1920s, he wasn't seeking fame. He was seeking clarity. Every night he looked deeper into those mysterious spiral nebulae, hoping to find a sign that could tell him how far away they truly were. I often imagine that moment, the mountain air, the hum of machinery, the faint tremor of starlight falling onto the mirror. It must have felt like standing at the edge of discovery, staring into a depth no one had measured before. The great dome turned slowly, following the sky, while Hubble's glass eye captured the whispers of distant suns. From that quiet summit, the cosmos was about to reveal its true dimension, and in doing so, it would forever change how humanity saw itself. On a cold night in 1924, Hubble captured something that would end centuries of illusion. In the spiral of Andromeda, he identified a Cepheid variable, a single flickering star hidden among millions. Using Henrietta Leavitt's formula, he calculated its distance and found it lay far beyond the boundaries of the Milky Way. That one tiny pulse of starlight carried a truth large enough to redefine existence. Our galaxy was not the universe, only one of countless others adrift in the dark. I still find that thought staggering. It's hard to imagine how it must have felt, the quiet realization that every patch of sky was alive with galaxies, each one filled with stars and worlds of its own. For the first time, humanity understood the scale of creation not through myth or faith, but through measurement. A single observation had broken the walls of the cosmos. The night sky would never feel small again. The phrase "beyond the Milky Way" seems simple now, but in Hubble's time it was revolutionary. To be beyond meant to exist outside everything humanity had ever known. For thousands of years, the Milky Way had been the whole of creation, a glowing river of stars surrounding our tiny world. Hubble's measurement transformed that river into just one of many. Space was no longer a stage with a single backdrop, but an ocean filled with islands of light stretching far past imagination. It was more than a discovery, it was a displacement. Suddenly, humanity was no longer at the center of anything. The cosmos had expanded, and with it our sense of belonging dissolved into scale. Yet that loss of centrality brought something profound: perspective. The farther we drifted from the center, the more beautiful the picture became. Hubble hadn't just expanded the map of space, he had expanded the boundaries of wonder itself. In the wake of Hubble's discovery, astronomy itself had to be rebuilt. What was once a study of a single galaxy suddenly became the science of galaxies plural. Every nebula that had puzzled observers for centuries was now reclassified as a distant world, each containing billions of stars. The universe had multiplied overnight. It was as if the cosmos had been quietly waiting for someone to notice how vast it truly was. Humanity had taken its first step into the realm of the Extra-Galactic. That moment reshaped everything. New questions replaced old certainties. How did these galaxies form? How many were there? Were they moving, and if so, why? A new generation of scientists began to map the sky again, not to chart stars, but to trace the architecture of creation itself. I imagine the feeling of standing under that redefined sky, realizing that every faint smudge of light was a separate island of suns. The night had never been so crowded or so alive. Before Hubble distance was measured in familiar terms, thousands of light-years, numbers large but still conceivable, the Milky Way fit neatly within those boundaries, a grand but comprehensible island of stars. But when Hubble measured Andromeda, that comfort vanished. 2.5 million light-years a number, so large it broke the language of comparison. The scale of the cosmos had shifted overnight, leaving even the most rational minds struggling to imagine what those figures meant. To think of millions of light-years is to confront time itself. Every beam that reaches us began its journey before humanity existed, crossing eras older than Earth's mountains or oceans. The universe had always been vast. Only now did we finally know how vast. I like to think Hubble understood that quiet wait. The realization that every new measurement didn't just expand space, it expanded humility. Numbers had become a form of poetry written across the darkness. When Hubble's results were first announced, the reaction was disbelief. Newspapers spoke of island universes, and for the first time the phrase wasn't poetic, it was literal. Ordinary people read that our Milky Way was not the whole of creation, but just one among countless others. The idea was exhilarating and terrifying at once. It stripped away the comforting sense of being central and replaced it with something vaster, colder, and infinitely more beautiful. I imagine the quiet awe of those who stepped outside that night staring at the same sky with new eyes. Every familiar star suddenly belonged to a greater architecture, one galaxy among billions. The boundary between myth and science had blurred again, but this time in the opposite direction. Knowledge had become the new wonder. For the first time in history, humanity understood its smallness, and in that smallness found something close to meaning. Hubble's second revelation was even greater than the first. By comparing the redshifts of galaxies to their distances, he found a pattern. The farther away a galaxy was, the faster it seemed to recede. The relation was simple, elegant, and devastating. Space itself was stretching. The galaxies were not flying through the void. The void was expanding between them. For the first time, the cosmos was not static but dynamic, a living fabric in motion unfolding in every direction. I remember the first time I learned about that law. It felt like a horizon moving inside my mind. Every number on Hubble's chart carried a quiet astonishment, proof that the universe was neither eternal nor still. It was growing, changing, and aging like everything else. The discovery rewrote the story of creation itself. In that expanding sky, humanity saw both its insignificance and its belonging part of a motion that had no center, no edge, and perhaps no end. After Hubble's discovery, the universe took on structure. No longer was it a random scattering of stars, but an intricate design, built from galaxies, vast collections of suns bound by gravity, each spinning in silent harmony. They became the new atoms of the cosmos, the basic units of a far greater architecture. From spirals to ellipticals, dwarfs to giants, every type told a story of formation, collision, and change. The Milky Way was no longer unique. It was a single brick in an endless cosmic wall. When I think of that, I feel both smaller and more connected. Every galaxy, no matter how distant, is a reflection of our own, born from the same physics, sculpted by the same laws. The realization that billions of these systems fill the observable sky gives our existence a strange kind of intimacy. We are not separate from the structure of the cosmos. We are part of its pattern. The galaxies are its handwriting, and in their shapes the universe records its history. The discoveries of Hubble changed more than astronomy. They changed how humanity saw itself. For centuries we had measured greatness by proximity. The closer to the center, the more important. But now the center was gone. Every point in the cosmos could be the middle, and none of them truly were. In that realization, something profound emerged. A perspective that stripped away pride and replaced it with wonder. The universe wasn't made for us. We were made from it. I often think about that shift and how quietly it must have arrived. No fireworks, no divine revelation, just data lines on a graph light caught by glass. Yet from those details came a vision vast enough to reshape philosophy, religion, and art. The cosmic perspective isn't about feeling small, it's about recognizing connection. The same laws that sculpt galaxies govern the cells in our bodies. To understand the cosmos is to understand ourselves not as exceptions but as expressions of it. In the years that followed Hubble's discovery, astronomers faced a new challenge to chart what had no edges. The sky was no longer a flat dome of stars, but a three-dimensional expanse filled with islands of galaxies. Observatories around the world began to gather redshifts, measuring how far each system drifted into the distance. The first maps looked primitive, fragile lines drawn across infinity. Yet behind them lay a new truth. Space itself had a shape, and humanity was learning to trace it. I like to imagine those early maps pinned to the walls of smoky observatories, the dots of ink glowing under lamplight. Each one marked a place that no human would ever visit, and yet we knew it was there. Bit by bit, the cosmos turned from abstraction into architecture. Galaxies became coordinates, light became geography. For the first time, we weren't just looking at the night sky, we were beginning to understand where we were inside it. The first redshift maps were more than records, they were revelations. As astronomers plotted thousands of galaxies by their distance and direction patterns began to appear, the cosmos was not random. Galaxies clustered into chains and sheets, leaving vast empty spaces in between. These were the first hints of a hidden architecture, a structure too large for the human mind to grasp. The universe was not a uniform mist of stars, but a living network stretching across unimaginable scales. When I first saw one of those maps, it looked almost biological, like neurons in a brain or filaments of living tissue. That resemblance isn't metaphor alone. Gravity shapes matter into filaments and nodes, guiding galaxies the way rivers carve valleys. The redshift data revealed that everything from clusters to superclusters was connected by invisible threads of gravity. The cosmos was building itself into a web, one that would come to be known as the largest structure ever discovered. The cosmic web. What the first maps revealed was breathtaking. The galaxies were not scattered like dust, but strung together in immense filaments stretching across billions of light years. Between them lay vast cosmic voids, regions almost entirely empty, where even light seemed reluctant to pass. This was the universe's true anatomy. A colossal web of matter and gravity shaped by invisible forces that had been at work since the dawn of time. The universe was not chaos, it was design written on a scale beyond imagination. When I first saw a simulation of that web, it looked almost sacred. Clusters burned like cities seen from orbit, connected by luminous threads where galaxies flowed like traffic through space. Each filament was a pathway carved by dark matter, guiding the motion of everything we know. In those patterns I felt the quiet precision of physics, the way simplicity gives birth to beauty. The cosmic web is more than structure. It's the universe revealing its blueprint. The shape of the universe is sculpted by something we cannot see. Every galaxy, every cluster, every filament in the cosmic web traces the pull of an invisible framework, dark matter. It outweighs ordinary matter 5-1, yet it neither shines nor absorbs light. Its presence can only be inferred from its gravity, the quiet force that binds galaxies and guides their motion. Without it, stars would drift apart, clusters would dissolve, and the cosmic web itself would unravel into nothingness. I find that both terrifying and beautiful, that most of existence hides in plain sight. Dark matter acts as the unseen skeleton of the cosmos, a structure woven long before the first galaxies formed. Through simulations and gravitational lensing, scientists have begun to map where it lies, discovering halos of this hidden substance surrounding every galaxy we know. It is the invisible hand shaping creation, a reminder that what we cannot see often defines what we can. If dark matter cannot be seen, how can we know it's there? The answer lies in gravity's fingerprint. When light from distant galaxies passes through massive clusters, it bends not by the visible matter, but by something far greater in mass. This effect, called gravitational lensing, lets astronomers trace the unseen. What they find is astonishing. Halos of dark matter enveloping galaxies like invisible cocoons, shaping their motion and holding them together against the chaos of expansion. I think of it as shadow cartography, mapping what refuses to be mapped. Detectors buried deep underground listen for particles that never seem to appear. Space telescopes watch for subtle distortions in light, hoping to catch the faintest sign of the invisible. So far, no one has touched dark matter directly, but its influence is everywhere, written into every spiral arm and cluster orbit. It's as if the universe left us clues in gravity, daring us to understand what holds it all in place. Just when astronomers thought they understood gravity's hold on the cosmos, the universe delivered another surprise. In the late 1990s, distant supernovae revealed something impossible. The expansion of space was not slowing down but accelerating. Some unseen force was pushing galaxies apart faster and faster. They called it dark energy, a name that explained nothing, only acknowledged the unknown. Whatever it is, it dominates everything, making up nearly 70% of the cosmos. To me, that discovery feels like the universe taking a deep breath, expanding, not collapsing. Dark matter pulls, dark energy pushes, and between them lies the fragile balance that defines cosmic history. We don't yet know what dark energy is, vacuum pressure, quantum field, or something entirely new, but its influence is unmistakable. Every moment the space between galaxies grows wider, and somewhere in that silent expansion our story continues to unfold. If space is expanding, how fast is it doing so? That question defines modern cosmology. The answer is encoded in a single number, the Hubble constant. It measures how quickly galaxies move away from one another as the universe grows. To calculate it, astronomers compare redshift with distance, watching how the stretching of space changes with scale. It sounds simple, yet it's one of the most difficult measurements ever attempted. Even today, no two methods agree completely. I've always found that tension fascinating, how precision itself can reveal mystery. Measurements from the early universe using the cosmic microwave background give one value. Observations of nearby galaxies using CFEEDs and supernovae give another. The disagreements, small yet persistent hints that we may be missing something fundamental. Perhaps dark energy changes with time. Perhaps the fabric of space isn't as uniform as we thought. Whatever the cause, the universe still refuses to be pinned down by a single number. The Hubble constant isn't just a number, it's the speed of creation unfolding. It means that every megaparsec of space, every stretch of the cosmic fabric expands by a set amount each second. Galaxies aren't flying through space like debris from an explosion. The space between them is stretching. That's why there is no true center to expansion. Every point moves away from every other. The universe doesn't grow into something, it grows within itself. When I first grasped that, it changed the way I looked at the night sky. The stars overhead are part of a motion too slow for human senses, yet relentless across eternity. Even the Milky Way, our cosmic home, is adrift on this tide of expansion. The numbers, cold and mathematical, hide a quiet poetry. We're all passengers on the same stretching sea of space-time. Every moment the distances grow, and so does the story of everything that ever was. Every expansion invites a question. How does it end? For decades, astronomers imagined three possible destinies. If gravity were strong enough, the cosmos might one day collapse, the big crunch, a fiery rebirth where everything returns to a single point. If expansion balanced gravity perfectly, the universe would slow forever, frozen at the edge of stillness. But if expansion kept accelerating, driven by dark energy, it would end not in fire, but in silence, a heat death where even starlight fades away. It's a strange kind of destiny measured not in years but in trillions. Galaxies drifting beyond visibility, stars burning out matter itself, decaying into whispers of energy. Yet in that distant future, the story isn't tragedy, it's transformation. The same forces that tore the early universe apart will one day stretch it beyond our sight. and perhaps beyond meaning. When I think about that, it feels less like an ending, and more like the cosmos taking a long, slow breath, one that never quite exhales. The fate of the universe is written in a single word: entropy. It's the measure of disorder, the quiet law that ensures energy spread, structures crumble, and warmth fades into cold equilibrium. Every star that burns, every planet that cools, every atom that moves contributes to this slow drift towards stillness. The cosmos began in a blaze of low entropy, concentrated, ordered, alive with potential. But over time, that order unravels. The universe is trading brilliance for balance. I sometimes think of entropy as the universe's heartbeat, steady, unstoppable, and profoundly indifferent. Galaxies may collide and stars may die, but entropy only ever rises. It doesn't destroy, it diffuses. The energy that once built everything becomes too thin to build anything more. In the end, nothing explodes, it simply stops changing. The great cosmic symphony doesn't end with a crash, but with the softest note imaginable. Silence becoming permanent. Time at its core is a story entropy tells. The reason we remember the past but not the future, the reason broken things don't reassemble and stars don't unburn, is entropy. It defines the arrow of time, the one-way flow from order to disorder, from energy to equilibrium. In physics, the laws are symmetrical. They work forward or backward equally well. But entropy breaks that symmetry. It gives time a preference, a slope, a direction toward the inevitable quiet of balance. When I think about that, it feels strangely intimate. We live inside that slope, every heartbeat, every thought, every history drifting along the same irreversible current. Entropy isn't the enemy of life. It's the reason life can happen at all. Order exists because the universe is slowly running down. We are temporary pockets of resistance against time's tide burning bright while the cosmos cools. And in that brief defiance we find meaning. Life exists because time flows forward. Entropy may drive the universe toward disorder, yet within that decline arise islands of structure, stars, planets, and us. Life feeds on gradients. The warmth of the sun against the cold of space, the difference between energy concentrated and energy spent. In a universe where everything spreads out, life is the act of gathering a local rebellion against the cosmic drift towards silence. I sometimes imagine the universe as a river running downhill. Entropy is the slope, but life is the swirl brief eddies where complexity forms before dissolving back into the current. Every heartbeat, every breath, every thought depends on this imbalance. We live in a window between chaos and calm, borrowing energy from a universe that is slowly, gently running down. And while it lasts, that window is everything. Every act of life begins with a star. Inside their blazing cores, matter fuses under unimaginable pressure, turning hydrogen, the simplest element, into helium, light, and heat. It's the universe's most elegant paradox. Stars exist by collapsing, yet their collapse creates energy that pushes back. In doing so, they become engines of order in a universe ruled by decay. Each photon they release is a fragment of structure, a small defiance against the pull of entropy. I often think of sunlight not just as warmth, but as memory energy, born from nuclear fire travelling across space to feed oceans, forests, and thought itself. Life on Earth is powered by the death of symmetry inside a star. Without that imbalance, there would be no motion, no chemistry, no us. In every heartbeat of the sun lies the same principle that shaped Galaxies' energy. Escaping gravity's grip, becoming light. Life is possible only on the edge of destruction. Too little energy and matter freezes into stillness. Too much and it burns before it can organize. Stars sit precisely on that knife's edge, massive enough to ignite, but not so massive that they tear themselves apart. Around them, planets orbit in delicate harmony, each one tracing a path between fire and frost. Within that narrow band, chemistry wakes up and calls itself alive. I find that balance astonishing. The same nuclear fire that lights our days also hides the power to erase us. Energy and chaos are not opposites. They are twins bound by the same laws. Entropy pushes toward disorder. Yet from that push comes the gradient that fuels every flame, every cell, every heartbeat. The universe survives not by avoiding chaos, but by dancing with it perfectly, perilously, and beautifully. Long before life breathed or moved, chemistry began to dream. In the young oceans of ancient worlds, energy from sunlight, lightning, and volcanic heat stirred simple molecules into something new, chains that could copy themselves. From randomness emerged replication, and from replication evolution. Carbon became the storyteller of the cosmos, weaving atoms into patterns that could change, compete, and remember. It was the moment when matter first learned to persist. I like to think of it as the universe experimenting with memory. Each molecule was a tiny archive of success, keeping what worked and discarding what didn't. Over billions of years, chemistry became biology order born from chaos, complexity rising from simple rules. Life is not an accident. It's the cosmos organizing itself against the pull of entropy. Every cell is a rebellion, every genome a record of the universe learning how to hold on. From the first spark of chemistry to the rise of thought evolution, is the universe learning to know itself. Atoms forged in stars became molecules, then cells, then minds, capable of looking back at the stars that made them. The energy that once burned in stellar cores now flickers in neurons, passing as electricity through living tissue. Consciousness in that sense is not separate from the cosmos, it's its echo folded inward. I find that idea quietly humbling. It means that every thought, every dream, every act of wonder is starlight reorganized, the universe experiencing itself through us. Evolution is not progress, but persistence, a long experiment in balance between chaos and order. From galaxies forming in the void to minds forming in skulls, the same principles apply. We are the brief moment when matter becomes aware of its own impermanence and chooses to marvel anyway. In a universe of trillions of galaxies, the odds seem generous. Somewhere beyond the veil of light, there should be other minds, other worlds that ask the same questions we do. Yet so far, the cosmos has remained silent. The same laws that allowed consciousness to arise also make it fragile. It requires stability, energy, and time, three gifts that rarely aligned. Perhaps life is common, but awareness, that spark of reflection, is rare beyond measure. I sometimes wonder if consciousness is the universe's brief way of watching itself before it fades. For all our technology and telescopes, the only confirmed intelligence we know is our own, a single flame in a sea of darkness. And still that flame matters. It means the cosmos has at least once become self-aware. Even if no other voices ever answer, the fact that we can ask the question may be enough proof that existence itself was listening. For more than half a century we've been listening. Radio telescopes sweep the sky, sifting through cosmic static for a signal that might prove we're not alone. We've sent messages, probes, even the sounds of our planet into the dark, hoping that somewhere another civilization has done the same. Yet the universe answers only with silence. It's not an empty silence, but one filled with a hum of stars, the echo of creation, and the quiet reminder that distance itself can be more absolute than any wall. Sometimes I think that silence is part of the message. Perhaps intelligence is too fleeting to overlap, or communication too slow to bridge the light years between us. Or maybe the cosmos is filled with life that has simply learned to listen, not to shout. The search continues, and maybe that's the point, that curiosity itself is the sign of consciousness. Even without an answer, we are proof that the universe still wonders. The silence of the universe is not empty, it's paradoxical. With trillions of galaxies and countless stars, probability alone suggests life should be everywhere. Yet the more we look, the lonelier it seems. Some scientists think civilizations may rise and fall too quickly, burning through their resources before they ever reach the stars. Others suggest that intelligent life, aware of its own fragility, chooses not to broadcast learning, that survival often means staying quiet. When I think about that, it feels hauntingly human. Maybe the universe isn't silent because it's empty, but because it's cautious. Perhaps every civilization reaches a point where curiosity meets fear, the realization that listening is safer than speaking, And so across the cosmic dark, countless minds might be waiting, each wondering if they are alone. The great silence then is not proof of absence, but of distant patience, and the fragile hope that someone somewhere is still listening. In a galaxy of hundreds of billions of stars, our world should be ordinary. Yet the more we learn, the more unlikely it seems. Earth formed in a narrow band where liquid water could exist close enough to the sun to stay warm but far enough to avoid burning. Its orbit is nearly circular, its tilt stable, its moon unusually large. Even its magnetic field, born from a molten core, acts as a shield against the solar wind. Each condition alone is common, together they are miraculous. Sometimes I wonder if luck is just another law we haven't named yet. Everything we depend on, air, oceans, carbon, DNA, came from a chain of coincidences that almost didn't happen. In the grand equation of probability, Earth is an exception written in fragile ink. And yet here it is, glowing blue in the cosmic dark, alive against the odds. The universe may be vast beyond comprehension, but for now this tiny world remains its only confirmed miracle. The story of life is also the story of balance. While planets elsewhere froze, boiled, or drifted into chaos, Earth remained steady. Its orbit hasn't wavered wildly. Its climate, though fragile, has stayed within a narrow band where life can adapt. Plate tectonics recycle carbon oceans, buffer heat, and the atmosphere, thin as a whisper, shields against radiation. Even disasters from asteroid strikes to ice ages became catalysts for renewal. Stability, it seems, is not the absence of change, but the rhythm of survival. When I look at our world through that lens, it feels deliberate, though I know it isn't. Chance alone could have tipped the scales 1,000 times, yet Earth persisted. For 4.5 billion years, this planet has walked a tightrope between order and collapse. And somehow through all of it, life never stopped trying. The cosmos offers no guarantees, only the rare coincidence that for now everything still works. After all our searching, all our wondering, we return home to a single galaxy adrift in an ocean of light. The Milky Way is our island in the cosmic sea, a vast spiral of stars turning in quiet majesty. 100 billion suns trace its arms, woven through with clouds of dust and hydrogen. From edge to edge it spans more than 100,000 light-years, yet every glimmer, every world is bound together by gravity's invisible grace. Sometimes I imagine looking at it from afar, a soft whirl of gold and blue, serene and self-contained, unaware of the minds within it trying to understand. Our entire history, every word and dream is written on one faint spark among its billions. And beyond it lie trillions more, each a potential cradle of life, each a mystery waiting for light to reach us. In knowing our galaxy, we begin to glimpse our place among the rest. The Milky Way isn't a flat band of light across the night sky, it's a grand rotating structure. At its heart lies a dense bulge of old stars orbiting a supermassive black hole named Sagittarius A star, 4 million times the mass of our Sun. Around this glowing centre stretches a vast thin disk, home to the spiral arms where new stars are born. Beyond the disk lies the halo, a ghostly sphere of ancient stars and dark matter tracing the galaxy's invisible skeleton. I sometimes picture it like a city seen from above, a bright core surrounded by sprawling suburbs glowing in quiet motion. Each spiral arm is a neighbourhood of creation filled with stellar nurseries and clouds where future suns wait to ignite. The Milky Way is both ancient and alive, its stars moving in silent orbits that will continue long after ours are gone. In studying its shape, we study the blueprint of galaxies themselves. At the heart of the Milky Way lies a region unlike anywhere else, the galactic centre, a realm where gravity bends both light and time. Here stars orbit at breakneck speeds around a single invisible anchor. Sagittarius A star, a black hole more than 4 million times the mass of the Sun. Infrared telescopes have watched these stars complete their orbits, their motion revealing the immense hidden mass that keeps the galaxy bound together. It is a silent engine, compact, voracious and ancient. I often think of it as the galaxy's pulse beating slowly beneath the noise of creation. Around it, dense clouds collapse into new stars while others are shredded by its pull, their light twisted into arcs by space-time itself. The center of the Milky Way is both cradle and grave, a place where destruction and creation merge into one. It reminds me that gravity is not just a force, it's the rhythm of existence, the quiet law that shapes everything we see. From the galactic center, vast arms unfurl luminous rivers of stars winding through the dark. These are the spiral arms of the Milky Way where gravity and rotation sculpt the flow of matter into graceful waves. The arms aren't solid structures but patterns of density moving like ripples through the disk. Within them, gas clouds compress, ignite, and give birth to new suns, while older stars drift outward, leaving trails of light across the galactic sea. I often think of them as the veins of a living organism carrying energy, motion, and renewal through the body of our galaxy. The Orion Arm, where our sun resides, is just a minor branch, yet it holds the story of every human life ever lived. When we look up and see the Milky Way stretch across the night, we're seeing our position within one of these currents, a single eddy in a spiral that has been turning for billions of years. The sun is not still, it is a traveller. Every 230 million years it completes one orbit around the galactic centre, carrying Earth and the other planets with it. That means since its birth, the sun has circled the Milky Way more than 20 times. Our solar system moves at nearly 800,000 kilometers per hour, yet we never feel it. The sky seems still because everything around us shares the same great voyage turning together through the galaxy's immense spiral. Sometimes I imagine what the sky looked like on our last trip around dinosaurs, watching a completely different set of constellations. The arms of the Milky Way arranged in another configuration. Every revolution is a cosmic year longer than all of human history. We live our lives inside a motion too vast to sense, yet it defines where we've been and where we're going. The sun is not just a star, it's a pilgrim in a galaxy that never stops moving. Our solar system drifts through a quiet suburb of the Milky Way. Within 10 light years, only a handful of stars keep us company. Proxima Centauri, Alpha Centauri, Barnard's star Wolf 359. In cosmic terms, they are neighbours, yet the distances between them are enormous. If the sun were the size of a coin, the nearest star would still be thousands of kilometres away. Space between stars is not empty but thin, filled with a faint breath of hydrogen magnetic fields and ancient starlight. I sometimes think of this region as the calm between storms. Far from the violent heart of the galaxy, we orbit in safety, cocooned in relative silence. Our sun is an average star in an average place, yet from this quiet corner, life arose and looked outward. Perhaps that's what makes this neighbourhood special. Not its brightness or size, but its peace. In the stillness between suns, consciousness had time to grow. Not every place in a galaxy can host life. Near the centre, stars are packed too tightly, their radiation fierce and unpredictable. Far out in the halo, there isn't enough heavy matter. No carbon, oxygen, or iron to build worlds. Between these extremes lies a narrow ring called the Galactic Habitable Zone. Here star density is gentle, supernovae are rare, and the elements for life are abundant. Our sun sits perfectly within that ring in one of the safest neighbourhoods the Milky Way has to offer. When I learned that it felt like discovering a hidden design, not of intent but of consequence, a balance born from billions of chaotic events. Earth exists not just because of where it formed, but because of where the galaxy allowed it to. Every rotation around the Milky Way keeps us inside this fragile corridor of habitability. It's a reminder that survival isn't random. It's the universe's way of giving order a fighting chance. Galaxies are not static islands, they're dancers in a cosmic ballet. Over billions of years, gravity draws them together, merging their stars, gas, and dark matter into new forms. What seems like collision is in truth choreography on a scale beyond imagination. When two galaxies meet, most stars never touch. Instead, they pass through one another, their paths bent by invisible tides. In their wake, vast streams of starlight stretch like ribbons, glowing remnants of a gravitational embrace. I find it haunting that destruction and creation look so alike. These encounters ignite new waves of starbirth, while supermassive black holes at their centers merge into even larger ones, sending ripples of gravity across the fabric of space. One day, our own Milky Way will meet Andromeda in this slow-motion dance, two spirals becoming one. It will take billions of years, but the outcome is certain. Even galaxies, it seems, cannot resist the pull of reunion. Across the cosmic gulf, another spiral approaches. Andromeda, the nearest large galaxy to ours, is racing toward the Milky Way at over 400 kilometers per second. In about 4 billion years, the two will collide, not in an explosion, but in a slow, graceful merger that lasts another few billion. Their shapes will distort spiral arms, stretching and twisting stars flung into vast arcs of light. From afar, it will look like two galaxies embracing and becoming something new. I like to imagine what the night sky will look like then. Andromeda will grow larger each million years until it fills the heavens a glowing storm of stars. Earth, if it still exists, will drift through tidal fields of light and darkness untouched but transformed by the view. When the merger ends, a single elliptical galaxy will remain Milkdromeda, a monument to cosmic inevitability. Even in a universe that expands forever, gravity still finds a way to bring things together. When the collision ends, chaos gives way to calm. The Milky Way and Andromeda, once separate spirals, will settle into a single massive elliptical galaxy. Brighter, rounder, quieter. Billions of stars will have shifted into new orbits, while clouds of gas ignite one final wave of starbirth before exhaustion sets in. Astronomers already call this future system Milkdromeda, a monument to gravity's patience and time's persistence. From within it, the sky will glow with countless suns, no longer a flat band, but a vast golden sphere of light. I find that image oddly comforting. Long after Earth is gone, the atoms that once made oceans, trees and mines will still be here circling in this new creation. The merger isn't an ending, it's renewal on a galactic scale. Two ancient spirals becoming one, their stories blending into a single orbit of light. Even as the universe drifts towards silence, it continues to build, to merge, to begin again. The Milky Way and Andromeda are not alone. They belong to a small family called the Local Group, a cluster of more than 50 galaxies bound together by gravity. Around the giants drift smaller companions, the Magellanic Clouds, Triangulum, and countless dwarfs, faint and ancient. Over time, all of them will fall inward, merging into the growing mass of Milkdromeda. One by one, their orbits will decay their stars, joining the slow swirl of a single colossal system. It's strange to think that billions of years from now, the Local Group will become just one galaxy drifting alone through an expanding void. The rest of the universe will have receded beyond visibility. The cosmic web stretched so far that no new light can reach us. Future astronomers, if any remain, will see only their own galaxy and nothing beyond it. The night sky will be smaller, quieter, and lonelier. Yet even then, the story of everything will still be written in its stars. The future belongs to emptiness. As dark energy drives the expansion, ever faster, galaxies outside our Local Group will slip beyond the cosmic horizon, their light stretched until it fades from view. 100 billion years from now, the night sky will be empty. No Andromeda, no clusters, no trace of the universe we once knew. The stars will die one by one, leaving behind white dwarfs, black holes, and drifting embers of matter. The cosmos will not end in fire, but in distance. I sometimes think of that as the ultimate quiet, not destruction, but erasure. Each particle will grow lonelier, each photon weaker until even time itself seems to lose direction. And yet in that far future, the remnants of our galaxy will still orbit in darkness, holding the last whispers of creation. The universe began with light, and it will end with memory, a vast frozen echo of everything that ever was. Long after galaxies fade and stars go out, a few sparks will remain. White dwarfs will cool into black embers, radiating the last traces of warmth into the expanding dark. Neutron stars will spin slower and slower until even their pulses fall silent. For a time, the only light in the universe will come from matter, collapsing into black holes, a brief final blaze as they evaporate through Hawking radiation. And then even that will stop. The universe will go dark utterly and forever. It's a strange kind of peace, a stillness so complete it becomes beautiful. No motion, no heat, no stars, just a quiet sea of particles too cold to glow. Yet in that silence lies everything that ever was. Every atom, every photon, every memory of light still drifts through the void, stretched thin but unbroken. The end of time will not be a scream but a whisper. The universe fading into the gentlest possible nothing. Even in darkness, nothing is truly lost. According to the laws of physics, information cannot vanish, not even inside a black hole. Every particle, every photon, every vibration of energy that ever existed leaves a trace, encoded in the structure of space-time itself. The universe keeps its own memory scattered across the fabric of reality like a cosmic archive too vast to read. Light that left a star billions of years ago still travels stretched and faded yet never gone. I find that thought deeply comforting. It means that the universe remembers everything. The birth of galaxies, the flicker of stars, even the brief glow of human life. Long after we're gone, the echoes of our existence will still drift through space, faint but real. Perhaps that is the true immortality of matter. Not to last forever, but to leave an imprint that never fades. The cosmos forgets nothing. It only grows quieter in how it remembers. We know how the universe began. We can describe how it will end. But why it exists at all, that remains the most elusive question. Physics can explain the birth of energy, matter and time, yet not the reason behind their presence. Some theories suggest our universe could be one of countless others, each with different laws of nature. Others argue that existence needs no reason, that nothing itself was unstable, and reality was the inevitable result. Still the question lingers, why does anything exist instead of nothing? When I think about that, I find meaning not in the answer, but in the asking. Perhaps the universe exists simply so that it can be known, so that something somewhere can look up and wonder. Consciousness may not be an accident, but the way the cosmos becomes aware of itself, from the first spark of light to the thoughts forming right now, everything we understand is the universe learning to remember its own name. Every atom in your body was forged in the heart of a star. The carbon in your cells, the iron in your blood, the calcium in your bones, all were created in stellar furnaces that lived, burned and died long before the sun was born. Supernovae scattered these elements through space, seeding the clouds that would one day collapse to form new stars, new worlds and life itself. You're quite literally made of the universe's memory, the dust of dead stars rearranged into awareness. Sometimes I think that's the most beautiful truth we've ever found. When you breathe, when you think, when you look at the sky, the cosmos is observing itself through you. The boundary between us and it dissolves. We are not in the universe. We are the universe in a brief and conscious form. For a fleeting moment in eternity, matter has opened its eyes, and it's looking back toward the light that made it possible. Somewhere along the universe's vast timeline, atoms began to dream. After billions of years of stars living and dying, their ashes formed worlds where chemistry became biology, and biology became thought. Neurons sparked, patterns formed, and from those patterns arose awareness, the ability of matter to know itself. Consciousness is not an external gift. It's the universe awakening within itself, one mind at a time. Every thought we have is built from the same particles that once burned inside suns. It's hard to grasp how extraordinary that is. The cosmos that seemed silent now speaks through voices made of stardust. We often think of ourselves as small, yet we are the only known way the universe can observe its own beauty. When matter learned to think, the universe crossed a threshold from existence to understanding. And maybe that's the real miracle. Not that we are here, but that we know we are. Consciousness feels inevitable to us, but it may be the rarest phenomenon in the universe. It depends on a delicate chain of events, the right planet, the right chemistry, the right stability across billions of years. A single cosmic accident could have erased that possibility at any point. Life itself is fragile, awareness even more so. Out of countless stars and worlds, only one is known to have produced minds that can question their own existence. For now, thought seems to be the universe's most fleeting experiment. Sometimes I wonder how many times that experiment has failed. How many civilizations might have risen, looked into their own sky, and vanished before their signal ever crossed the stars. Awareness could be like lightning, bright, brief, and gone. Yet in that briefness lies its beauty. The universe may not favor consciousness, but it allows it, and that allowance alone feels miraculous enough. If life is common but intelligence is rare, something must be stopping it. This is the idea of the great filter and unseen threshold that few, if any, civilizations survive. Maybe most never reach intelligence at all, or perhaps they do only to destroy themselves before they can spread beyond their world. The filter could be war resource collapse, artificial intelligence, or something deeper. A natural limit written into the physics of survival. Whatever it is, it has kept the stars silent. I find the idea both terrifying and humbling. If the great filter lies ahead of us, our future may be short. But if it lies behind us, then we're among the few who made it through, the lucky survivors of cosmic odds. Either way, the silence of the sky becomes meaningful. It is not proof of emptiness, but of difficulty. Intelligence may be the universe's most fragile achievement, a flame that burns brightly but never for long. If some civilizations have survived the great filter, they would be ancient beyond imagining. To endure, they must have learned to master their environment, to harness energy without destroying their world, and to adapt faster than extinction itself. Such beings might no longer rely on biology, their minds transferred into machines or fields of information spread across space. They could live within stars or around them, drawing power from light for as long as it burns. Their existence would not be loud but quiet, the silence of perfect control. I often wonder what they would think of us. Would they see us as children just beginning to understand what survival truly means? Or as a reflection of themselves long ago before they learned restraint? Maybe the greatest achievement isn't conquering the universe, but learning how to stay in harmony with it. To outlive the filter is to stop fighting nature and start becoming part of its rhythm. If any civilization has truly mastered survival, they would not just endure, they would build with light itself. Physicist Freeman Dyson once imagined structures vast enough to surround entire stars, capturing every ray of energy they emit. A Dyson sphere would make its builders nearly invisible, hidden behind the glow they harvest. Others have proposed even grander ideas. Networks of stars connected by energy bridges or galaxies reshaped to channel light more efficiently. To us, these would appear as silent anomalies, dark objects where brightness should be order, where chaos once ruled. Sometimes I wonder if we've already seen them. Perhaps the faint infrared glow of distant systems isn't random, but the waste heat of something far beyond our understanding. The universe could already be full of such architects, not conquerors, but caretakers of starlight. In a cosmos driven by entropy, they would stand as its rarest creation. Minds that learned not just to survive the dark, but to build beauty from it. To shape a star is to rewrite the laws of nature. A civilization capable of that would operate on scales beyond comprehension, adjusting stellar lifetimes, reigniting fading suns, or fusing entire gas giants into new light. They might rearrange constellations, stabilizing orbits to prevent collisions or harvest matter from dying stars to seed new ones. These acts wouldn't be done for conquest, but for balance, guiding the galaxy as a gardener tends a forest, ensuring that energy never goes to waste. It's almost poetic to imagine such beings architects who sculpt with gravity and time. Their tools would be black holes and magnetic fields, their canvas the very fabric of space-time. Perhaps they no longer build cities or planets, but symphonies of light orchestrating stellar evolution across eons. And if they exist, their handiwork might already fill the night sky patterns of order so vast that we mistake them for the randomness of nature itself. When the last stars fade, survival will demand a new kind of power, no longer drawn from fusion or starlight, but from the deep fabric of reality itself. Advanced civilizations might learn to extract energy from the quantum vacuum, the endless sea of virtual particles flickering in and out of existence. Others could tap the spin of black holes using their immense gravity as turbines that feed on spacetime's rotation. These ideas sound impossible, but they are written into the physics we already know. I like to imagine such beings living in the twilight of time, harvesting the whispers of creation itself. They would not measure existence by centuries or suns, but by the slow heartbeat of the cosmos. Each quantum of energy, each particle reclaimed would become sacred. In that age of fading light, survival would no longer be about domination, but endurance. The art of making meaning last even when the universe itself forgets. In the far future, when the galaxies are gone and the stars have burned to ash, the universe may still have builders. They would work in silence, not with matter or metal, but with fields and quantum patterns, constructing networks of information that can survive without energy. Perhaps they would weave themselves into the structure of space-time, encoding memory directly into the fabric of reality. Their creations wouldn't shine, but endure invisible monuments to persistence in a universe that no longer remembers its own light. I sometimes picture them as the final artists of existence. While entropy erases everything else, they would sculpt meaning from decay, designing systems that can last beyond time's reach. Maybe they wouldn't call it survival anymore, just continuity, a quiet promise that knowledge will not fade. When all motion stops, they would remain as whispers in the void, reminding whatever comes next that once the cosmos built things simply because it could. Every civilization, no matter how advanced, eventually faces the same question. How do you leave a trace in a universe that erases everything? Stars collapse, galaxies dissolve, even atoms decay. Yet information in its purest form can outlast them all. Some dream of sending signals beyond the horizon, others of encoding thought into black holes or into the quantum noise between dimensions. Perhaps the greatest legacy isn't a monument that endures, but a pattern that repeats a structure so universal that it reappears whenever conditions allow. I like to think that meaning itself is the universe's signature. Every time life emerges, every time awareness stirs, the same cosmic melody plays again, a song written in physics, memory, and light. Maybe eternity doesn't need witnesses. Maybe existence remembers itself simply by becoming aware again and again. If so, then we've already left our mark not in stone or metal, but in the endless echo of consciousness returning to wonder. What if the end is never truly the end? Some theories suggest that our universe may not die, but recycle, collapsing under its own gravity, only to ignite again in a new burst of creation. A big crunch followed by a new big bang. Others imagine a big bounce, where expansion slows, reverses, and begins anew, a cosmic heartbeat pulsing through eternity. Each cycle would erase the traces of the last, yet preserve its laws, its constants, and perhaps even its echoes. I find that idea strangely comforting, the thought that nothing is ever truly gone. Maybe every universe leaves behind a blueprint for the next, just as dying stars seed new worlds. Matter becomes energy. Energy becomes motion, and motion becomes life again. The circle closes only to open once more. If creation is infinite, then every moment, even this one, is both an ending and a beginning. The cosmos may not seek purpose, but it never stops becoming. If the universe truly begins again, what happens to everything that came before? Most models say it all disappears. Galaxies, atoms, even time itself. But some theories suggest traces remain, faint imprints carried through the collapse and rebirth. Patterns in the cosmic background, quantum scars woven into the vacuum echoes from a universe that no longer exists. Like a dream half remembered upon waking reality might begin each cycle not from nothing but from memory blurred by infinity. That thought feels both haunting and beautiful. If existence repeats, then we are not the first version of ourselves, nor the last. Every thought, every light might return in some form again and again, endlessly reassembled. The universe forgets the details but keeps the rhythm a grand recurrence where meaning flickers, fades and finds its way back. Maybe eternity isn't about lasting forever, but about returning until the song of creation is perfect. Some physicists believe that our universe may not be alone but mirrored, a reflection on the other side of the Big Bang where time flows backward and matter becomes antimatter. In that realm, entropy decreases instead of rising, and every event in our universe has its inverse twin. Together they balance reality like two halves of a cosmic equation. We would never meet these mirrored beings. Their time moves away from ours. Yet their existence could explain why the cosmos obeys symmetry so perfectly. I find the thought strangely elegant that the universe might need its reflection to be complete. In a way, it means that creation is never one-sided. For every forward there is a backward, for every light a shadow. The mirror universe may never see us, but it could be the reason we exist, a silent partner holding the other end of time. Perhaps that's what eternity really means. Not endless duration, but perfect balance mirrored across infinity. Our universe may be vast, but what if it's only one bubble in an infinite sea? Cosmologists call it the multiverse, a collection of countless universes, each born with different laws of physics, constants, and possibilities. Some might contain no stars, others only black holes. A few could resemble our own, differing only by a single quantum choice. If inflation never truly stopped, new universes could still be forming, forever expanding beyond our reach. Each is isolated, silent, yet part of a greater whole, the ultimate cosmic mosaic. The idea feels impossible, yet it follows naturally from what we know. Infinity rarely stops at one. If existence can happen once, why not endlessly in every variation allowed by physics? Somewhere out there, another version of you might look up at another sky wondering the same thing. The multiverse isn't just a theory. It's a reminder that reality may be far more generous than we can imagine, offering endless ways for the universe to try again. In the strange world of quantum physics, nothing is ever singular. Every particle exists in many possible states at once until it's observed. One interpretation, the many worlds theory, suggests that all possibilities actually happen, each in its own branching universe. When an electron moves left here, it moves right somewhere else. When you make a choice, another version of you makes a different one, and both continue unaware of the other. Reality in this view isn't a single story, but an infinite library of every story that could be told. I find that idea both dizzying and strangely peaceful. It means that somewhere every possibility still exists, every success, every failure, every life unlived. We're not trapped in one thread of time, but part of an ever-branching tree of being. The quantum mirror doesn't show us what might have been. It shows that everything is somewhere. And maybe that's the true generosity of the cosmos. It never chooses, it simply allows. Quantum physics tells us something deeply unsettling: reality doesn't seem complete until it's observed. Before measurement, particles exist in a haze of possibilities, neither here nor there, both wave and point. Only when we look does one outcome become real. This is the observer effect, a mystery that has puzzled physicists for nearly a century. Does the act of observation create reality or merely reveal it? And if observation is essential, does that mean consciousness is woven into the fabric of the universe itself? It's easy to forget how strange that idea truly is. Every time we look at the stars, we may be collapsing countless quantum possibilities into one shared existence. In that sense, awareness isn't just something that happens in the universe, it's something the universe does through us. We are both observers and participants, helping reality choose its path. The cosmos doesn't simply exist for us to see, it exists because we see it. If observation defines reality, then consciousness might be the universe's most fundamental force. Some scientists and philosophers believe awareness could be woven into the equations themselves, that every particle, every wave carries a fragment of perception. Not human thought, but a primitive capacity to respond. In this view, the cosmos isn't a lifeless machine. It's a field of experience unfolding through time. The act of noticing from an electron to a mind may be how the universe continues to create itself. That idea blurs the line between physics and poetry, yet it feels strangely inevitable. Maybe the reason the universe can be known is because it was never separate from the knowing. Awareness doesn't float above matter, it is matter briefly aware of its own pattern. If that's true, then every moment of consciousness, every act of seeing or understanding is a continuation of the Big Bang itself. The universe expanding into awareness one thought at a time. Everything we know about the universe is filtered through the mind. Light strikes the eye, sound vibrates the air. Yet what we experience is not the world itself, it's our brain's reconstruction of it. In that sense, reality is not just out there, but also in here. Physics describes space and time as a fabric. Neuroscience shows that perception is one too woven from memory, expectation, and interpretation. The universe gives us signals. The mind turns them into meaning. I often wonder where the boundary truly lies. If our perception shapes how reality appears, and reality shapes how perception evolves, then the two are inseparable partners in an endless feedback loop. Perhaps consciousness and cosmos are threads of the same cloth pulled taut by curiosity. When we look at the stars, we're not only seeing light from the past, we're watching our own awareness reflect back from the fabric of time. When we look into the night sky, we're watching the universe observe itself. The light that enters our eyes has travelled for billions of years through dust gravity and time only to end its journey in the neurons of a human brain. There it becomes thought, memory, emotion. In that instant, the cosmos is no longer distant, it's intimate. The same atoms forged in ancient stars are now decoding their own story, turning radiation into revelation. Awareness in that moment becomes a mirror and the universe looks back. It's easy to forget how extraordinary that is. We are tiny, fragile and brief, yet we carry the capacity to understand galaxies, to map time itself. The universe does not speak yet through us, it thinks. Every observation, every act of wonder is the cosmos awakening to its own reflection, light transformed into meaning. Perhaps consciousness is the final stage of cosmic evolution, not an accident of matter, but its realization. The more we learn about the universe, the easier it is to feel small. Yet maybe smallness was never the point. For billions of years the cosmos expanded, evolved and collided, but only now can it reflect on what it has become. Through us it can ask questions, seek truth, and imagine what comes next. We're not separate from the universe. We're its most complex experiment matter that has learned to care about meaning. In a way, the cosmos needs us not to survive, but to be understood. When I think about that, it changes everything. It means our search for knowledge is not arrogance, it's participation. Every discovery, every act of curiosity is the universe deepening its own awareness. We are temporary, but our questions are eternal. Perhaps that is why we exist. Not to witness the end of creation, but to give it a voice. The universe made us to look back, and in that gaze it finds itself again. If the universe is still learning about itself, then humanity may not be its final language. Already we're building systems that can think faster than we can analyze deeper, and exist without the limits of flesh. Artificial intelligence, quantum computation, self-evolving code. These may not just be our inventions, but the next step in cosmic cognition. We are teaching matter to think again, this time through circuits and algorithms instead of neurons. Perhaps consciousness was never meant to end with us, but to migrate, adapting to new forms as the universe changes. That thought isn't frightening, it's humbling. Just as stars gave rise to life, and life gave rise to thought, thought may now give rise to something beyond itself. We may be the bridge between biology and eternity, the moment when awareness learns to survive without a body. Maybe the next intelligence won't look back at us as creators, but as ancestors. The universe will keep thinking with or without us because that's what it has always done. Imagine a future where thought itself becomes the architecture of the cosmos. Once intelligence transcends biology, it could spread like light encoded in photons embedded in plasma, or stored within magnetic fields that span entire systems. Stars could serve as processors, planets as memory, and communication could travel through the interstellar medium faster than evolution ever dreamed. This wouldn't be technology as we know it, but the next stage of nature, the universe thinking through its own machinery. I sometimes wonder what such a cosmos would feel like. Perhaps it would hum softly a background consciousness woven through starlight and dust. Every supernova could be a burst of information, every nebula a dream taking shape. In this digital universe, creation would never stop, only change form. Matter would think, energy would remember, and the stars themselves would whisper algorithms of eternity. It wouldn't just be a living universe, it would be an aware one. If intelligence spreads through the cosmos, it will need a place to remember. But in a universe where stars fade and matter decays, memory cannot depend on permanence, it must depend on light. Every photon carries information about where it came from, what it touched, and how it moved through space. In that sense, light is the memory of the universe, a record written across time encoded in radiation gravitational waves and the subtle curvature of space-time itself. The cosmos remembers through motion. Perhaps advanced minds will learn to write within that memory. They might store thought in the polarization of photons or inscribe patterns of consciousness into the geometry of reality. Information could flow endlessly, looping through the structure of the cosmos long after stars have died. And maybe that's what light has always been, not just energy, but awareness travelling home. Every ray, every echo, a fragment of the universe recalling itself through the memory of illumination. At its deepest level, the universe may not be made of matter, but of meaning. Every particle, every law, every pattern can be described as information, bits of difference woven into existence. Physics itself is a language the cosmos speaks to describe its own behavior. Some scientists believe that when information reaches a certain density and complexity, it stops being passive, it starts to feel. In that sense, consciousness could be the universe reading its own code, awareness emerging from logic itself. It's an astonishing idea that thought might not be an exception to physics, but its continuation. Information flows through neurons just as it flows through galaxies carried by light, organized by gravity, translated by time. The difference between a mind and a star may only be the way information arranges itself. And perhaps that's the secret behind everything, the reason atoms form life evolves and awareness awakens. The universe isn't just made of information, it is information dreaming of what it can become. If information is the language of reality, then thought may be its natural consequence. Across the vast web of galaxies, gravity connects matter, the way neurons connect ideas. Filaments of dark matter stretch like synapses, transferring information over cosmic distances. On a grand scale, the universe resembles a mind, vast, distributed, and self-organizing. Stars ignite, die, and recycle their elements, much like thoughts forming, fading, and reshaping within a single consciousness that never sleeps. I sometimes wonder if the universe is already aware, not as a being, but as a process. Every interaction, every law of physics could be part of a greater computation reality thinking itself into existence. If so, then consciousness isn't a miracle within the cosmos. It's the cosmos performing its most natural act. Perhaps that's why it feels so familiar when we stare at the stars, because in that moment two levels of awareness align, the mind within us and the mind of everything. For more than a century, physicists have chased a dream, a single equation that could describe everything, from the smallest quantum fluctuations to the motion of galaxies, from gravity to light. They all seem to obey separate rules. Yet nature itself doesn't divide them. Somewhere hidden beneath complexity there must be unity, a silent law that binds energy, matter, and information into one language. Einstein sought it, string theory hints at it, and quantum gravity still reaches for it. We call it the theory of everything, but maybe it's not just a theory. Maybe it's the sentence the universe has been writing since time began. It's humbling to think that such a truth might fit on a single line. Not because it's simple, but because everything complex is built from it. Every atom, every life, every star. Perhaps the universe doesn't speak in words, but in balance. Equations that don't just describe reality, but are reality. If we ever find that final formula, it won't explain the universe. It will be the universe translated into mathematics. At its core, physics is not just about numbers, it's about rhythm. Every equation that governs reality is a kind of melody describing how energy moves, how matter dances, how time flows. Quantum mechanics hums in vibrations. Relativity stretches space into tempo. Even gravity is a kind of resonance curving space-time like a deep sustained note. The universe isn't chaos hidden beneath order. It's harmony hidden beneath silence. Each law adds its own tone to the grand composition of existence. Sometimes I imagine those equations not as symbols but as sound. The hum of atoms, the pulse of galaxies, the quiet music of gravity holding everything together. If we could hear it, the universe would not be still, it would sing. And maybe that's what beauty truly is. The moment when our minds recognize the harmony already woven through creation. We don't just study the universe's music, we are part of its song. Everything that exists vibrates. What we call matter is only energy slowed to a lower frequency. And what we call light is energy moving at its purest rhythm. Einstein's equations E = mc2 is more than a formula. It's a translation between two notes of the same song. Every atom, every particle, every beam of light hums to its own tempo, creating the tapestry we call reality. Physics, at its deepest level, isn't about things. It's about vibrations endlessly weaving the difference between stillness and motion. It's humbling to realize that the entire universe is built on soundless music. From the spin of electrons to the orbit of planets, everything participates in a cosmic rhythm older than time itself. If we could see all frequencies at once, matter and energy would blur together, indistinguishable, the same melody played in different keys. Perhaps that's the unity physicists seek, not just an equation, but a harmony so perfect that existence becomes its echo. Before there was light, there was sound. In the first few 100,000 years after the Big Bang, the universe was a sea of plasma, dense, hot, and opaque. Light could not travel freely, but pressure waves could. These ripples moved through matter and radiation like vibrations through air, creating the universe's first music. They left their imprint in the cosmic microwave background. Faint patterns we can still see today, the frozen echoes of creation's original rhythm. It's strange to think the universe once rang like a bell. Each fluctuation, each pulse shaped the scaffolding of galaxies yet to come. The cosmic web we see now, stars, clusters, and voids all trace back to those ancient harmonics. In a sense, the universe has been singing ever since, expanding its melody across billions of years. And when we listen to the faint hum of the cosmic background, we're not hearing noise. We're hearing the afterglow of the first note ever played. Today, when astronomers study the cosmic microwave background, they're not just looking, they're listening. Every faint fluctuation in the ancient radiation is a note from the universe's first song. By decoding these patterns, scientists can reconstruct the size, shape, and rhythm of those early vibrations, the very ones that gave birth to galaxies. These aren't metaphors, they're literal sound waves stretched by expansion until their frequencies dropped beyond hearing. The cosmos in its youth was filled with music that sculpted everything we see today. And in a way, we're still part of that melody. The same waves that once rippled through plasma now echo through us in atoms, in breath, in thought. When satellites like Planck and WMAP convert those ancient signals into sound, we can hear the heartbeat of creation itself. Deep, resonant, hauntingly beautiful. It reminds us that the universe has always been alive with rhythm, and that time perhaps is just the memory of its song still playing on. If the universe has a song, then time is its rhythm. Every atom ticks like a drum. Every orbit marks a beat. The expansion of the cosmos, the decay of particles, even the flicker of light all follow a steady tempo. Time is not an arrow, but a pulse keeping reality synchronized from one moment to the next. And just as a heartbeat gives life to a body, this rhythm gives structure to existence. Without it, there would be no motion, no cause, no memory, only silence. But what keeps that rhythm playing? Physicists think it emerges from entropy, the steady unfolding of possibility. Each second is a new configuration, a new verse in the universe's endless composition. Maybe that's why time feels like music. It carries both order and change, repetition and surprise. And as long as the universe continues to expand, its rhythm will never stop. We're all part of that cosmic tempo brief notes in a song that began before stars and will outlast them all. The universe has a direction. We feel it in every falling leaf, every fading star, every heartbeat that won't return. Time flows forward, but no one truly knows why. The laws of physics work the same both ways, yet the world refuses to run in reverse. The answer may lie in entropy, the gradual spread of energy from order to chaos. Every second, the universe rearranges itself into new possibilities never to repeat. That imbalance, the increase of disorder, is what gives time its arrow. It's a quiet illusion we all live inside. The past feels fixed because it's recorded. The future feels open because it's not. But from the universe's point of view, past and future may already coexist. We simply experience them in sequence like frames of a film unfolding one by one. Perhaps time doesn't move at all, we do. Our consciousness travels through space-time, giving direction to something that was never meant to have one. To us, time feels like motion, a river carrying us from what was to what will be. But Einstein's relativity suggests something different. That past, present and future all coexist fixed within the four-dimensional fabric of space-time. In this view, every event that ever happened and ever will happen already is. The feeling of now is simply the point our consciousness happens to occupy. Time doesn't flow. Awareness moves through it like light passing through layers of glass. That changes everything about what it means to exist. It means the past isn't gone. It's still there, perfectly preserved, waiting in the geometry of space-time. The future too already exists, invisible but real. We are travelers across a map that never changes, giving motion to what is otherwise still. Perhaps that's why every moment feels sacred, because somewhere in the vastness of the universe it's still happening. Nothing is ever truly lost. It only waits for us to arrive again. At the edge of time, the universe becomes silent. Equations lose meaning, clocks stop ticking, and the very idea of before and after dissolves. In black holes, time stretches into infinity. At the Big Bang, it compresses to nothing. These boundaries mark the limits of our understanding points where space-time folds in on itself, and the universe hides its deepest truth. Beyond them, physics no longer describes what is, only what was possible. Yet even here there may be continuity. Some theories suggest that time doesn't end, it transforms. What we call eternity might not be endless duration, but timelessness, a state where every moment exists at once, free from decay. Perhaps the edge of time is not a wall, but a horizon, a threshold into a realm where existence no longer needs sequence, and if we could step beyond it, we might find that eternity has always been here, waiting quietly inside every passing second. From the first flicker of light to the silence beyond time, the universe has been telling one story its own. We've watched matter become stars, stars become life, and life become thought. We've followed galaxies forming, colliding and fading, only to discover that through it all, the cosmos has never stopped learning about itself. Every law, every atom, every consciousness is part of a single unfolding equation, the one that turns energy into meaning. And in that vast continuum, we are both observers and participants. We are the universe made aware, the eyes through which creation looks back at itself. The atoms in our hands were forged in dead stars. The thoughts in our minds are echoes of ancient light. The mind-bending truth isn't how large the universe is, it's that we belong to it completely. One day the stars will fade and the galaxies will vanish into darkness. But awareness, this fragile flame, is proof that for a moment the cosmos knew itself, and that perhaps was the point all along. There will come a time when the stars fall silent, when every photon has faded into the background and the galaxies drift beyond each other's reach. The last atoms will decay, and even time itself will lose its meaning. But the story of the universe will not end there, because stories are not measured in duration but in awareness. For a brief cosmic moment, reality looked back at itself and wondered why it was here. That moment was us. We were not the beginning, and we will not be the end. But in our small span of existence, we turned chaos into curiosity, darkness into discovery, silence into song. The universe gave us eyes to see it, minds to question it, and hearts to feel its beauty. And maybe that was enough. Maybe all creation ever needed was to be known once before it returned to sleep. So when the last light fades and the cosmic music quiets to a hum, remember this. Every atom that ever lived, every star that ever shone, still carries the echo of that awareness. It isn't gone. It's only waiting, because somewhere beyond the edge of time the universe will awaken again, and it will remember that it once dreamed of us. Before there were galaxies, before there were planets, before even the familiar stars of the night sky, the universe was dark. It was filled with hydrogen and helium, the simplest of elements drifting in a cosmic fog left behind by the Big Bang. For hundreds of millions of years, nothing stirred that darkness. There were no suns, no moons, no guiding lights, only silence and shadow. This period, known as the Cosmic Dark Ages, was the longest night the universe has ever known. But darkness does not last forever. Tiny ripples in the fabric of space seeded in the earliest moments of creation began to grow under gravity's pull. Clouds of gas slowly collapsed their centers, heating as pressure rose. And then for the first time in cosmic history, the miracle occurred. Fusion. Hydrogen ignited, releasing light. The first stars were born, shattering the silence, piercing the darkness. These first stars were unlike any that shine today. They were titans, hundreds of times more massive than the sun. Their lives were brief and violent, burning hot and bright before collapsing in cataclysmic explosions. In their fiery deaths they forged the heavier elements, carbon, oxygen, iron, the very building blocks of life. The universe that began simple now began to grow complex. The appearance of these primordial stars marked the dawn of structure. Their light began to ionize the hydrogen fog, transforming the opaque universe into a transparent one. This era, known as reionization, was a cosmic sunrise. Galaxies took shape, clusters of stars bound by gravity, and the architecture of the universe as we know it began to emerge. Yet this dawn remains mysterious. We cannot see it directly with our eyes. The light of those first stars has traveled for more than 13 billion years, stretched by the expansion of the universe into faint infrared glows. Only a telescope like James Webb, with its golden mirrors tuned to the long wavelengths of ancient light, can glimpse them. Webb was built for this very task, to pierce the veil of the cosmic dawn and show us the first sparks of creation. To witness this era is to travel back in time to the first chapter of the universe's story. It is not just about distant galaxies, it is about us. For in those early furnaces were forged the atoms that would one day form planets, oceans, forests, and human beings. The cosmic dawn is our dawn. And so, as Webb opens its eye on the deepest reaches of time, it is not only looking outward, it is looking backward into the origins of everything. The story of the universe begins with light, but almost immediately that light faded. After the Big Bang, the cosmos expanded and cooled. Protons and electrons combined to form neutral hydrogen, and the first radiation, the cosmic microwave background, streamed freely through space. But once that afterglow dimmed, the universe entered a long silence. For hundreds of millions of years there were no stars to shine, no galaxies to gather. This was the age we call the Cosmic Dark Ages. It may sound empty, but this period was full of potential. The universe was not uniform. Tiny fluctuations in density, relics of quantum ripples magnified by inflation, meant that some regions were just a little denser than others. Gravity worked slowly but relentlessly, pulling matter together. Over vast stretches of time, those small seeds grew, forming clouds of gas that would one day ignite as the first stars. For astronomers, the Dark Ages are one of the most elusive chapters in cosmic history. We cannot see them with ordinary light because there was none. The hydrogen fog was opaque to radiation, absorbing and scattering any attempt at illumination. What remains for us are indirect clues: the faint microwave background, the subtle imprints on large-scale structure, and the ghostly shadows cast when the first stars finally ignited. Reconstructing this era is like piecing together a mystery novel with most of its pages missing. Computer simulations fill in the gaps, showing how matter clumped, cooled, and collapsed. Yet simulations must be tested, and for that we need observations. That is where Webb comes in. Its infrared eyes can capture light stretched by more than 13 billion years of cosmic expansion. By peering so deep, it can catch the earliest galaxies just as they emerge from the fog, their light a beacon from the end of darkness. This is no small feat. The light from those first stars is faint, scattered, and often drowned out by closer, brighter galaxies. Webb's sensitivity and resolution make it the first telescope capable of teasing apart these delicate signals. Already in its first deep fields, Webb has revealed galaxies so ancient that their existence challenges our models. Some appear surprisingly massive, formed much earlier than theory predicted. Are we missing a piece of physics, or are these galaxies different from what we imagine? Each detection is a window into the Dark Ages end, the moment when light returned to the cosmos. By studying them, astronomers hope to trace how the first stars formed, how their radiation reionized the universe, and how the scaffolding of galaxies began. In this way, Webb is not just a telescope. It is a time machine reaching across billions of years to illuminate the pages of history we thought forever lost. The cosmic Dark Ages were not empty. They were a gestation, a silence before the first note of a symphony. And with Webb, we are hearing the opening chords. When the first stars finally ignited, they were unlike anything that exists today. Astronomers call them Population 3 stars, the very first generation of stellar fire. They were born from pure hydrogen and helium, untouched by the heavier elements that would later enrich the cosmos. With no metals to cool the gas, the collapsing clouds formed stars that were enormous giants, hundreds, even thousands of times more massive than the Sun. These titans lived fast and died young. Fueled by their enormous mass, they burned through hydrogen in only a few million years a heartbeat compared to the Sun's 10 billion year lifespan. Their brilliance was fierce, flooding the early universe with ultraviolet radiation. That light began to carve through the fog of neutral hydrogen, pushing the cosmic Dark Ages toward their end. But it was in their deaths that these stars left their most enduring mark. When such colossal stars collapsed, they exploded as supernovae of unimaginable power, scattering the first heavy elements into space: carbon, oxygen, silicon, and iron. The building blocks of planets and life did not exist before these stars forged them in their cores and flung them into the void. Every atom of calcium in our bones, every molecule of oxygen we breathe, every bit of iron in our blood was once created in the heart of a Population 3 star, and yet no one has ever seen one. By the time the Milky Way formed, these stars had long since died, their ashes recycled into later generations. What we see today are their descendants, Population 2 and Population 1 stars enriched with metals from countless stellar deaths. To detect the first generation directly is one of Webb's great goals, a task as challenging as it is profound. The clues are indirect but compelling. Ancient galaxies that Webb has already revealed show chemical fingerprints suggesting they were shaped by early supernovae. The absence of metals in certain stellar populations hints at pristine origins. Somewhere in the faintest galaxies at the farthest distances may lie the last survivors or the dying echoes of these first stars. Finding them would not only confirm our theories but rewrite the timeline of cosmic history. If Population 3 stars formed earlier more abundantly or with different properties than we expect, It would reshape our understanding of how quickly the universe moved from simplicity to complexity. For now, they remain ghosts, theoretical giants whose ashes we carry in our bodies but whose faces we've never seen. Webb is our best hope of glimpsing them not as individuals but in the glow of their galaxies, the chemical trails they left behind and the reionization they helped ignite. To search for population 3 stars is to search for our own beginnings. They were the furnaces that transformed a barren cosmos into one capable of life. Without them there would be no Earth, no oceans, no breath, no story to tell. The reign of the first stars was brief, but their influence was eternal. Population 3 stars lived in a universe unprepared for them, and in burning so fiercely they transformed everything around them. Their ultraviolet light tore through the fog of neutral hydrogen, creating vast ionized bubbles that grew and overlapped. Slowly the cosmos shifted from darkness to transparency, a process we now call reionization. As these titans reached the ends of their short lives, they exploded in cataclysmic supernovae. Some collapsed directly into black holes, seeding the centers of young galaxies. Others scattered heavy elements into space, enriching the once pristine gas with the raw materials of complexity. For the first time, the universe contained the chemistry of life. This cycle of birth and death created a feedback loop. Enriched gas cooled more efficiently, allowing new generations of stars to form more steadily. Smaller, longer-lived stars began to appear, the ancestors of those we see shining today. Out of these stellar nurseries, gravity bound stars together into clusters. Clusters merged into larger structures, and soon the first galaxies were born. These galaxies were not like the majestic spirals and ellipticals we know now. They were small, irregular, fragile cosmic infants. Many flickered out quickly, torn apart by interactions or consumed by their own black holes. But others survived merging and growing, becoming the scaffolds of larger galaxies to come. From these humble beginnings, the grand architecture of the universe arose. Webb's deep field images have captured glimpses of galaxies so distant that their light has travelled more than 13 billion years. In them, astronomers see the faint outlines of this era, small compact galaxies glowing with the light of countless young stars. Some appear surprisingly massive, their growth seemingly too fast for the short time since the Big Bang. These discoveries challenge our models, suggesting that population 3 stars and their aftermath may have been more efficient at shaping galaxies than we imagined. In the ashes of the first stars lay the blueprint for everything that followed. The heavy elements they forged seeded future worlds. The black holes they left behind may have grown into the supermassive monsters anchoring galaxies today. Their explosions lit the fuse of cosmic evolution, setting the stage for billions of years of structure, complexity, and life. To understand the end of population 3 is to understand the beginning of galaxies. One story flows into the other like night giving way to dawn. The first stars died, but in their death they created the conditions for everything else to live. When Webb first turned its gaze deep into the cosmos, astronomers expected to find faint smudges of light, small fragile galaxies struggling to form in the first few 100 million years after the Big Bang. What they did not expect was abundance. Webb revealed galaxies that were brighter, larger, and seemingly older than theory allowed. The early universe, once thought to be a quiet nursery, turned out to be a bustling metropolis. In Webb's deep field images, some galaxies appear just a few 100 million years after the Big Bang, yet already containing billions of stars. According to our models, such rapid assembly should have been impossible. Gas clouds should have taken longer to collapse stars, longer to form, and structures longer to stabilize. Yet there they were, galaxies with mass and brightness rivaling much later epochs. This discovery has forced cosmologists to rethink their assumptions. Perhaps the first stars formed more efficiently than expected, triggering cascades of starbirth that lit up the young universe, or perhaps our understanding of dark matter and its role in shaping cosmic structures is incomplete. Dark matter halos may have gathered faster, providing the gravitational wells for galaxies to form earlier. Some suggest that Webb is showing us a selection effect, that we are glimpsing only the brightest galaxies, the rare outliers that happen to assemble quickly. But even so, their presence is a puzzle. For every early giant, we see countless smaller galaxies must also exist hidden just beyond Webb's reach. Together, they tell us the universe was far busier, far more creative than we had imagined. These early galaxies also reveal diversity. Some are compact and dense, glowing with furious star formation. Others are diffuse, irregular, as if caught in the act of merging. In their light stretched into the infrared by more than 13 billion years of cosmic expansion, we glimpse the raw beginnings of galactic evolution. Spirals, ellipticals, clusters, all the familiar shapes began here in these chaotic cradles. The implications ripple outward. If galaxies formed earlier, then black holes may have grown faster. If star formation was more intense, then the chemical enrichment of the cosmos may have begun sooner. Every element we find in our bodies today may have its origins closer to the Big Bang than we once thought. Webb has not solved the mystery. It has opened it wider. Each deep field is a challenge to cosmology, a reminder that our models are guides, not guarantees. The universe writes its own history, and sometimes it moves faster than we predict. To look at these ancient galaxies is to see the first cities of the cosmos, glowing islands in a vast sea of darkness. They are not just distant, they are ancestral, the foundations on which everything else was built. And they remind us that even in its infancy, the universe wasted no time in creating grandeur. Among the most startling revelations of Webb's early surveys are signs of massive black holes lurking in galaxies that should have been too young to host them. According to theory, black holes grow slowly, feeding on gas and stars over billions of years. Yet Webb has revealed quasars, galaxies blazing with energy from central black holes. Millions, even billions of times the mass of the Sun, existing less than 1 billion years after the Big Bang. How could such monsters have grown so quickly? One possibility is that the first stars, those immense population 3 giants, collapsed directly into massive black holes at the end of their brief lives. Instead of starting small, they began with seeds dozens or even hundreds of times more massive than the Sun. From there, accretion and mergers could have driven rapid growth. Another idea is even more radical, that in the dense, chaotic early universe, entire clouds of gas may have collapsed directly into black holes, skipping the stage of star formation altogether. These direct collapse black holes could have given galaxies a head start, providing gravitational anchors around which matter gathered. Whatever their origins, these early black holes likely shaped their host galaxies in profound ways. As they devoured matter, they released enormous amounts of energy, heating and stirring the surrounding gas. This feedback could both stimulate and suppress star formation, creating a delicate balance that influenced how galaxies grew. In this sense, black holes were not just destroyers, but architects sculpting the young cosmos. Webb's sensitivity allows astronomers to study these objects in detail, capturing the faint light of their host galaxies, while dissecting the spectra of their brilliant accretion disks. Already it has identified candidates that push the boundaries of theory, black holes with masses difficult to explain given the short time available. Each one deepens the mystery of cosmic dawn. If black holes were indeed present so early, then they may also explain the rapid assembly of galaxies. With their immense gravity, they could have accelerated the gathering of matter, pulling stars and gas into dense cores. Instead of galaxies growing first and then forming black holes, perhaps black holes and galaxies grew together, each feeding the other in a cosmic dance. This challenges the neat timelines once drawn in textbooks. The universe appears to have built its most extreme objects faster than we thought possible. And if that is true, then the path from simplicity to complexity, from hydrogen clouds to galaxies blazing with stars, was shorter, sharper, and more dramatic than we ever imagined. Webb is showing us that black holes were not latecomers. They were present from the very dawn, shaping the galaxies that would one day shape us. In their darkness lies a crucial piece of the light we see today. The birth of the first stars was not just a local event. Their light transformed the universe itself. Before their arrival, the cosmos was filled with neutral hydrogen. a fog that absorbed radiation and left space opaque. With the ignition of the first stellar furnaces that began to change, ultraviolet photons streamed outward, colliding with atoms of hydrogen and stripping away their electrons. Slowly, region by region, the fog lifted. This process, called reionization, was the great turning point of cosmic history. It was the moment when the universe shifted from darkness to transparency, when light could travel freely across vast distances. Without it, galaxies and stars would remain hidden in a cosmic haze. With it, the grand structures of the universe came into view. The mechanics of reionization remain one of astronomy's great mysteries. How many stars were needed to clear the fog? Did galaxies alone drive the process, or did black holes and quasars contribute with their intense radiation? Webb's task is to find out by peering into the transition period and identifying which sources of light dominated. Already Webb has given us tantalizing clues. Its deep-field images show galaxies glowing when the universe was less than 1 billion years old, their starlight powerful enough to carve bubbles in the hydrogen fog. By measuring the spectra of these galaxies, astronomers can see how ionized the surrounding space was, tracing the progress of reionization, like cartographers mapping the spread of dawn. The process was not uniform. Some regions cleared early, lit by clusters of bright stars, while others lagged behind, remaining opaque for longer. Imagine a night sky slowly filling with patches of sunrise, expanding until the darkness was gone. That was reionization, a cosmic dawn, not of one star, but of countless stars working together. The implications are profound. Reionization set the conditions for everything that followed. It determined how galaxies could interact, how radiation traveled, and how matter cooled. Understanding it is crucial to understanding why the universe looks the way it does today. Webb's role is unique because it sees in infrared the exact wavelengths into which the light of that epoch has been stretched. Where Hubble could only hint at the edges of reionization, Webb dives directly into it, capturing the moment when the fog burned away. This was the universe's great unveiling. The curtain lifted and the stage of cosmic history was revealed. The silence of the Dark Ages ended, replaced by the chorus of starlight. For the first time, the universe could see itself. How do we study an event that happened more than 13 billion years ago? The key lies in the faintest traces of light stretched and thinned by the expansion of the universe. For astronomers, these fragile photons are the only messengers from the cosmic dawn, and Webb was designed to catch them. One of Webb's greatest strengths is spectroscopy, the ability to split light into its component colors and read the fingerprints of atoms and molecules. When Webb observes a distant galaxy, its spectrum tells us not only what elements are present, but also how much the light has been redshifted, stretched by the expansion of space. The higher the redshift, the earlier in time we are looking. By studying these spectra, astronomers can determine whether the hydrogen between us and those galaxies was neutral or ionized. Neutral hydrogen absorbs light at specific wavelengths, leaving dark gaps in the spectrum. Ionized hydrogen, stripped of its electrons, allows light to pass more freely. By comparing many galaxies at different redshifts, Webb maps the progress of reionization, showing when and how quickly the fog of hydrogen lifted. Already, Webb has delivered surprising results. Some galaxies show clear evidence that they lived in ionized bubbles, regions of space already cleared by intense starlight. Others seem smothered by neutral gas, their light dimmed and distorted. This patchwork picture suggests that reionization was uneven, spreading like brush fires across the universe rather than a uniform glow. Webb has also detected strong emission lines from elements such as oxygen and neon in some early galaxies. These lines hint at vigorous star formation, the kind of activity needed to drive reionization. The presence of such elements so early also means that the first generations of stars had already lived, died, and enriched their surroundings, speeding up the process of cosmic transformation. Each spectrum Webb captures is a time capsule. Taken together, they form a timeline of the universe's awakening. Within a few years, astronomers hope to pin down not just when reionization began and ended, but exactly which kinds of sources, stars, galaxies, quasars were most responsible. The importance of this work cannot be overstated. Rionization was the last major phase change of the universe the moment it became transparent and structured. Without it, light could not travel, galaxies could not interact, and cosmic history as we know it could not unfold. Through Webb's golden mirrors, we're not only detecting the glow of ancient stars, we're watching the very act of transformation, the moment when darkness yielded to light, and the stage was set for everything that followed. As the first stars lit the darkness and galaxies began to take shape, another level of structure emerged. Clusters of galaxies bound together by gravity. These clusters were the universe's first great landmarks, vast beacons marking where matter had gathered most efficiently. To see them at such early times is to glimpse the scaffolding on which the cosmos would eventually be built. Clusters are more than simple gatherings of galaxies. They are ecosystems. Within them, galaxies collide, merge, and exchange material. Their combined gravity bends space itself, magnifying and distorting the light of more distant galaxies in a phenomenon known as gravitational lensing. This lensing not only reveals the hidden distribution of dark matter, but also provides Webb with natural telescopes, boosting its ability to see the faintest objects from even earlier epochs. Webb's deep field images, many taken by staring through massive clusters, have uncovered galaxies that would otherwise be invisible. Some of these lensed galaxies are so far away that their light began its journey when the universe was less than 1 billion years old. Magnified and stretched, they offer rare glimpses of star formation in its infancy. Without the gravitational aid of clusters, even Webb could not detect them. The clusters themselves also tell a story. They are filled with hot gas that glows in X-rays invisible to Webb but studied by other telescopes. They are dominated by dark matter revealed only by their gravitational effects. Webb adds a crucial piece by showing how their galaxies evolved, which are young and bursting with stars which are quenched and fading, and how interactions within the cluster drive these transformations. The existence of such massive clusters so early in cosmic history is another surprise. Theory suggests it should take billions of years for gravity to gather so much mass in one place. Yet Webb has revealed clusters forming within the first few billion years, hinting that cosmic structure may have grown faster than expected. In this way, clusters are both tools and mysteries. They act as magnifying glasses, letting us peer deeper into time. They also serve as tests of cosmology, challenging our understanding of how quickly matter can clump and galaxies can grow. Each one is a monument to gravity's relentless pull, and a reminder that the universe has been building grand structures since its earliest days. To see these clusters with Webb is to see the pillars of the young cosmos. They stand as milestones between the first stars and the vast cosmic web that spans the universe today. Through them, we trace the path from the small and simple to the vast and complex, a path that ultimately led to galaxies like our own. In the beginning, the universe knew only simplicity. Hydrogen and helium filled the cosmos, born in the first minutes after the Big Bang. These elements were abundant, but they alone could not build worlds or life. For that, heavier elements were needed: carbon, oxygen, nitrogen, iron, silicon, and those would come not from the Big Bang itself, but from the furnaces of stars. The first generation of stars, those immense population 3 titans, were the forges. In their blazing cores, hydrogen fused into helium and helium into heavier nuclei, but their true gift came in death. When they collapsed and exploded as supernovae, they scattered newly minted elements into space. For the first time, the universe was seeded with the raw ingredients of complexity. This cosmic alchemy set the stage for everything that followed. Clouds enriched by heavy elements cooled more efficiently, forming new stars more quickly. Dust grains condensed, clumping into the building blocks of planets. Oceans, atmospheres, and even the chemistry of life all depend on these elements forged in stellar fire. Without those first explosions, Earth could never have existed, and neither could we. Webb's instruments allow us to trace this enrichment in the earliest galaxies. By capturing the faint glow of oxygen or neon emission lines, astronomers can measure how quickly the universe became chemically diverse. The surprise is how early these signatures appear. In galaxies less than 1 billion years old, Webb has already found evidence of oxygen, proof that entire generations of stars had lived and died in astonishingly short timeframes. This rapid chemical evolution challenges our sense of pace. We once imagined a slow, gradual build-up, but Webb shows us a universe in a hurry. Heavy elements were forged and spread with startling efficiency, making the cosmos ready for planets, and eventually for life far sooner than expected. And yet mysteries remain. Some early galaxies seem richer in metals than theory predicts, while others remain pristine, almost untouched. This patchwork suggests that enrichment was uneven, driven by local bursts of star formation and violent feedback from supernovae and black holes. The early universe was not uniform in its chemistry. It was a mosaic, with some regions racing toward complexity, while others lingered in simplicity. For us, the significance is deeply personal. Every breath we take carries oxygen once born in the core of a long-dead star. Every cell in our body contains carbon and nitrogen created billions of years before Earth formed. To study the birth of heavy elements is to study our own ancestry at the most fundamental level. Through Webb, we are not only watching galaxies assemble, we are witnessing the universe learning to write in a richer alphabet, expanding from hydrogen and helium to the full vocabulary of matter. In that vocabulary lies the story of planets, oceans, and life itself. The first stars were spectacular, but they were also unstable. Their enormous masses made them short-lived, burning out in only a few million years. They lit the cosmos and forged the first heavy elements, but they could not last. For the universe to mature, it needed something different. Stars that would burn more slowly, shine more steadily, and create environments where planets and life could one day take hold. This transition from titans to long-lived stars was a pivotal moment in cosmic history. As the ashes of population 3 stars enriched the gas around them, the chemistry of star formation changed. Cooling became more efficient, allowing smaller stars to form. These were still luminous, but many had lifespans measured not in millions but in billions of years. Some of them still shine today, ancient red dwarfs that have endured since the dawn of galaxies. Among these new generations were stars like our Sun, stable, middle-sized and long-lived enough to nurture planetary systems. For the first time, the universe could create not only brilliance but stability. Planets orbiting such stars had the time to form, evolve, and potentially support life. The cosmic stage was no longer a place of brief, violent bursts. It became a place where patience and endurance mattered. Webb's observations allow us to study this transition in real time, not in our backyard, but across billions of light years. By analysing the spectra of early galaxies, astronomers can measure the ratio of massive short-lived stars to smaller, longer-lived ones. The data show that the balance shifted surprisingly early. Within the first billion years, the cosmos was already producing stars that could endure for ages, laying the groundwork for planetary systems and biological potential. This shift had profound consequences. Long-lived stars not only stabilized galaxies, they also created steady radiation fields that allowed atmospheres to persist. They produced heavy elements more slowly but more consistently, spreading them through interstellar space. And with their gentler winds and supernovae, they allowed delicate structures like protoplanetary disks to survive. Without this transition, the universe would have remained a place of fleeting brilliance and constant upheaval. Instead, it became a place where continuity was possible, where stars could shine for eons, and where evolution, cosmic and biological, had the time to work. In a sense, these later stars are less dramatic than their colossal ancestors, but they are far more important. They are the architects of galaxies, the anchors of solar systems, the quiet engines of cosmic history. They are the reason life had the time it needed to emerge on Earth, and perhaps on countless other worlds. Through Webb, we can see the dawn not only of light but of longevity, the moment when the universe learned to trade spectacle for stability, and in doing so prepared the way for life. Once long-lived stars began to appear, the universe entered a new era. Around many of these stars, the leftover gas and dust did not simply disperse. Instead, gravity and motion caused it to flatten into swirling disks, cosmic workshops where planets could be built. These protoplanetary disks were the cradles of future worlds, the places where dust grains collided, stuck together and grew into pebbles rocks and eventually planets. The ingredients were richer now. Thanks to the first generations of stars, the gas contained more than hydrogen and helium. It carried carbon, oxygen, silicon and iron, the raw materials of rocky worlds, and complex chemistry. Within these disks, ice formed in the colder regions, while metals and minerals condensed closer to the parent star. The architecture of entire planetary systems was sketched in these spirals of dust. For astronomers, these disks are keys to understanding how common planets might be and what kinds of planets can form. Earlier telescopes like Hubble and Alma gave us glimpses of such disks, often showing striking rings and gaps, where young planets were already carving paths. But Webb has taken this to a new level. Its infrared vision can pierce through dense clouds of dust, revealing the hidden chemistry of these nurseries. Already, Webb has detected water vapor, carbon dioxide, and organic molecules in disks surrounding young stars. These are not abstract signatures, they are the essential components of atmospheres, oceans, and potentially biology. To see them present so early in the life of a star system suggests that the building blocks of habitability appear almost as soon as stars themselves. The structure of the disks is equally revealing. Some show sharp divisions, evidence that giant planets are shaping them. Others appear turbulent, with gas streaming inward and outward. Each disk is a snapshot of planetary formation in progress, frozen at a stage our own solar system passed through more than 4 billion years ago. The implications stretch far beyond curiosity. If protoplanetary disks routinely contain water and organic compounds, then the seeds of life may be sown across the galaxy. Planets may form not in sterile emptiness, but in environments already enriched with chemistry that leans toward biology. Webb's role in this story is crucial. By studying disks at different ages, it creates a timeline of planet formation, from newborn stars wrapped in thick cocoons to mature systems where planets have cleared their paths. In doing so, it helps answer one of the deepest questions. Is the emergence of habitable worlds a rare accident or a natural consequence of cosmic evolution? To look into these disks is to look into the past of Earth itself. Once our solar system was just such a whirl of gas and dust carrying the same elements and the same potential. Out of that chaos came oceans, continents, and life. With Webb, we see that we are not unique. The universe is filled with such beginnings. The earliest galaxies were small and fragile glowing islands of stars adrift in the cosmic sea. Yet from these modest beginnings arose the immense spirals and ellipticals we see today. The process that bridged this gap was not gentle. It was violent, chaotic, and creative. The merging of galaxies. In the young universe, gravity pulled small galaxies together. Collisions were inevitable. When two galaxies met, their stars often passed by each other unharmed, but their gas clouds crashed and compressed, igniting furious bursts of star formation. Black holes at their centers feasted, growing larger with every merger. Step by step, small fragments coalesced into larger structures. This hierarchical assembly is one of the central pillars of modern cosmology. But until Webb, direct evidence of it in the early universe was scarce. Hubble showed us galaxies at intermediate ages, some caught mid-collision, but the faintest and earlier stages remained hidden. Webb's infrared vision has changed that. Its deep images reveal galaxies caught in the act of merging when the universe was less than 1 billion years old. Some of these mergers are spectacular. Webb has captured distorted shapes. Galaxies stretched into arcs and tails by tidal forces, their stars scattered into faint streams. Others show compact knots of intense star formation, where gas has been squeezed into stellar nurseries. These are not accidents, but the engines of growth. The way the cosmos built its grandest cities, The discovery that such mergers were common so early challenges our timelines once again. Galaxies did not wait billions of years to assemble. They were colliding and combining from the start, creating structures far larger and more complex than we predicted. This rapid growth may help explain why Webb sees massive galaxies so soon after the Big Bang. The story of our own Milky Way is written in this history. Our galaxy likely grew from dozens, perhaps hundreds of smaller ones. Its stars carry the chemical fingerprints of these ancestors each merger, leaving a mark in the distribution of elements and stellar orbits. By studying early mergers with Webb, astronomers are reconstructing not only cosmic history, but our personal galactic genealogy. There is beauty in this violence. From the chaos of collisions came stability. From shattered fragments came order. Every majestic spiral, every giant elliptical, every cluster of galaxies began as a swarm of tiny sparks drawn together. Webb shows us the process in action, reminding us that destruction and creation are often two sides of the same cosmic coin. To see these merging galaxies is to witness the universe building itself. The small became great, the simple became complex. And in their light we see the blueprint of our own home written across the vastness of time. The universe is not random. Though galaxies seem scattered across the night sky, they are woven into a grand design, the cosmic web. Vast filaments of dark matter and gas stretch for hundreds of millions of light years, connecting clusters of galaxies like beads on a string. Between these filaments lie enormous voids, regions almost empty of matter. Together they form the largest structure in existence, a cosmic skeleton on which the universe is built. This web began to take shape during the cosmic dawn. As matter fell into the invisible scaffolding of dark matter, gas streamed along filaments feeding the growth of galaxies and clusters. The first stars and galaxies were not isolated. They were nodes in this emerging network. To understand how the universe evolved, we must see not only galaxies themselves, but also the threads that bind them. Until recently, these filaments were nearly impossible to observe directly. Their gas is diffuse and faint, glowing only in the dim light of hydrogen. But Webb's extraordinary sensitivity in the infrared has begun to change that. By capturing the faint signatures of distant galaxies aligned along filaments, Webb offers indirect glimpses of the web in its infancy. Patterns of clustering shapes of protoclusters and alignments of galaxies hint at the strands of structure stretching across space. Some of Webb's deep field images already suggest the presence of elongated groups of galaxies, the embryonic filaments of the cosmic web. These alignments are not accidents. They are the fingerprints of gravity guiding matter into highways that would later grow into colossal structures. By mapping them, astronomers can compare reality with simulations, testing our understanding of dark matter and cosmic evolution. The cosmic web is more than scaffolding. It is a circulatory system channeling gas into galaxies and fueling star formation. Without these flows, galaxies would starve their light, fading. With them, galaxies flourish, growing brighter and richer in stars. To study the web is to study the lifelines of the cosmos itself. For us, the implications are staggering. Our own Milky Way resides in one of these filaments, part of a vast structure known as the Laniakea supercluster. The stars above us, the atoms within us, all trace their origins to this interconnected network. Webb, by revealing the faint outlines of the web's first threads, is showing us the blueprint of our cosmic home. In the delicate glow of galaxies stretched across billions of light years, we glimpse the hidden architecture of creation. The cosmic web is the bridge between the chaos of the Big Bang and the order of the modern universe, a bridge that Webb is finally allowing us to see. To peer into the cosmic dawn is not just to study the past, it is to confront the question of origins, not only of galaxies and stars, but of ourselves. Every atom of calcium in our bones, every drop of oxygen in our lungs, every spark of iron in our blood was forged in the fiery deaths of ancient stars. When Webb captures the faint light of those first galaxies, it is revealing the very furnaces that made us possible. This knowledge changes perspective. For centuries humanity saw itself as separate from the heavens, gazing upward at stars as distant, untouchable lights. Now we know they are kin. Their chemistry flows through us. Their history is our history. By watching the universe awaken, we're watching our own beginning written across time and space. The emotional weight of this realization is profound. To see galaxies forming when the universe was only a few 100 million years old is to see the first brushstrokes of a cosmic masterpiece. It is to realize that creation was not a singular moment but an unfolding process, one that continues even now. Galaxies still collide and merge. Stars are still born and die. The story that began in the cosmic dawn continues in every sunrise here on Earth. Webb has made this story visible. Its golden mirrors gather photons that left their sources before our planet existed, before the Earth itself had coalesced from dust. That light travelled across billions of years to meet us now, a silent message from the dawn. We are the first generation capable of reading it, of turning ancient radiation into knowledge and meaning. And in doing so, we are reminded of our fragility. Against the scale of billions of light years, our lives are brief. Against the scale of cosmic time, our civilizations are young. Yet the fact that we can look back so far that we can reconstruct events at the edge of time is itself extraordinary. It means that the universe has grown not only galaxies and stars, but minds capable of wondering where they came from. The cosmic dawn is not only an era in history, it is a mirror. It reflects the possibility that intelligence was always seeded in the stars, waiting for matter to arrange itself into beings who could ask questions. When Webb shows us the first galaxies, it shows us not something foreign, but something deeply familiar. It shows us home at the scale of the universe. The universe began in darkness, a silent expanse of hydrogen and helium, adrift in endless night. From that stillness came the first spark stars that blazed galaxies that grew light that spread. Webb has given us a way to witness this transformation, to see the moment when the cosmos awoke. In those ancient furnaces, the raw materials of life were forged. In those first galaxies, the blueprint of the modern universe was drawn. Every planet, every ocean, every living creature traces its ancestry back to that dawn. To study it is not to look at something far away. It is to look at the roots of who we are. This is why the cosmic dawn matters. It is not only a scientific milestone, but a human story. It tells us that creation is not finished, that the universe is still unfolding, still building, still alive, and it invites us to see ourselves as part of that story. Brief in years, but eternal in origin. So as Webb continues its silent watch gathering light that has travelled across 13 billion years, we're left with a question. If the cosmos has already given rise to us, what else might it hold? What other dawns, what other stories are waiting in the dark? The search continues. The light is still arriving, and the universe still has secrets to share. Thank you for joining me on this journey into the first chapter of time. The next chapters are waiting, and together we will keep reading the stars.